Okay, we'll get started. Good afternoon, everyone, to this afternoon session, which is session 2 of day 2 of VLSI conference tutorial. And we have two speakers for this session today. Uh, one is Kostas Doris, Dr. Kostas Doris from Netherlands, is in NXP. And we have second speaker, Preet Yadav. So the topic of today is more like automotive market and automotive segment. This is divided into two parts. Part one will be shifting more on automotive from mechanical to electrical, okay, and evolution of his next generation automotive architecture. The second part will be covered by Dr. Kostas Doris, and that will mostly on the millimeter wave CMOS automotive radar, okay. So these are the two part. We'll take a break at 3 p.m. Short 15-minute break for tea and coffee, and after that, Dr. Kostas Doris will continue. We'll start with Puneet Yadav, and he will cover the shift of automotive from mechanical to electrical. Okay. So I just wanted to give a quick introduction about the speakers. So the first go with Dr. Kostas Doris. So Dr. Kostas Doris is actually fellow in NXP, Netherlands, and he's also a part-time professor at the Technical University of Eindhoven. He's co-author of many papers, several papers and patents, including the books in the field of the data converter and millimeter wave radar. Okay, he's currently leading the RF SOC automotive radar transceiver innovation activity in NXP, and also he do the teaching activity at university. Okay. He's actually part of the various committee and the technical program committee and at the regional EU chair as well. And he's also for the associate editor of the IEEE transaction of circuit and systems. So our next speaker is actually Preet Yadav. So he's R&D associate technical program manager for automotive group in NXP Semiconductors. So he'll priority NXP. He was actually working as Wipro, and he's actually involved in many of the committee and fellow of the IEEE. Okay? He's associate editor of the IEEE Sensor Alert as well. Okay, he's chairman of IEEE Circuit and System Society of Delhi chapter, and also a member of the global IEEE CASS. Okay, so which is VLSI System Application and Technical Committee. So with this short introduction, I will invite Preet Yadav to give his session on shift of automotive from mechanical to electrical.
Okay. Good afternoon. Can you guys hear me? Well, on each of the corners, left and right and center. I assume these are 3 different conference rooms and they're collaborated up together to make a large hall here. Okay, great. So thank you so much for showing up for this post-noon session with a delicious meal. Gajar ka halwa in the sweet dish, am I right? Gulab jamun. Oh, they served me something different then. Great. So let me first, take pleasure, opportunity, and honor to introduce Kostas Doris. He's an XP fellow based out of Eindhoven, Netherlands, which happens to be our headquarters and very well-known face in the whole technical fraternity. So he's come all the way from Eindhoven to share his knowledge with all of us. So thank you so much. So the way we have planned this whole next 3 hours is that I'll bore you for the first 90 minutes, and then he will certainly enrich you with a lot of good stuff around radar in the next 90 minutes post the tea break. Zoom videos here. Oh, okay. Hey. Yeah, so that's how we split it up. So I'll start with the first 90 minutes, and we are going to talk about majorly the shift from mechanical to electric mobility, and we'll talk about a few of the topics as we move forward, and then we'll break for tea and coffee. Do come back because the next speaker is Kostas. Okay, and he'll focus on all the good innovations at NXP which we are doing around the radar. Okay, thank you. Thanks, Kostas. Great. So the new era of automotive mobility. So mobility is there, and I'm really fond of asking questions. and I'm really bad at answering them. Okay, so I'll try my best to give a appropriate answer to any of your questions, and try to do the best justice to it. But if I don't have answer, I'll make sure that I get back to you with the right answers. But I'll keep on asking a few questions as we move forward. Okay. So please raise your hands if you know the answer, and then probably one by one you can speak up instead of speaking in the crowd. Okay. So when I say mobility, can you make out what is the very first thing which comes into your mind? The very first, I would say, means of mobility. The very first means of mobility which strikes your mind when we talk about mobility. You need to just raise your hand. You need to just raise your hands. You need to just raise your hands. Yeah. Okay. Yes, sir.
Aircraft, airplanes.
Aircraft, airplanes. That's the very first mobility thing which you can think of or heard about.
Means it is widely used.
Widely used. Great. Thanks.
Electrons. Electrons.
Electrons. Amazing. I got B grade in my, physics of semiconductors. That's a bad part. The good part is the grading started from B itself. My professor, I was doing my master's back at Thapar University Patiala, and our professor Chatterjee, he decided that none of us deserve A grade, so he started grading from B. And I was lucky to be part of that B grade. Okay, great. Electrons mobility. So this reminds me one more thing. I was at Siri Pilani, that's a CSIR R&D lab of Government of India. And this scientist with whom I was working, he said, until unless you realize there's a hole being created and electron is moving, you don't stop, reading physics of semiconductors. I could not see that hole in the last 20 years. Don't go and tell this to my supervisor, Process applies to you. Okay, that's a good one. Anyone else? Mobility, very first thing of mobility. Walking, excellent. So how do I make this mechanical walking to electric walking is a big question to me. But yeah, anything else? Movement. Okay. I'm asking the means of mobility. No one said, invention of wheels, right? Car. Cart. So me and Costas, we were at Falaknama Palace last evening for a dinner, and we saw that tanga there, horse cart, and they said if you book a room, you get a horse cart. If you just come here for a meal, they give us this golf cart. Excuse. Good one. Anyone else? Last round. We have some chocolates for the good questions. I'll sponsor. Not worry. Okay. So to me, the very first mobility which comes to my mind, and I don't have those slides here specifically just to save time, is that magic carpet which flies in here. Aladdin. I think that was the very first thing if I can think of, someone moving from place A or destination A to destination B. Okay, and then the gradually wheel comes up. If I'm not wrong, the very first wheel I read again somewhere was being discovered somewhere in Slavonia, back in Europe. Okay, but the origins are, there are different kinds of wheels. Earlier, it used to be, wheels made of wood, and then many other metal and other things. Okay, excellent. So here I'm not talking about that magic carpet. We'll only talk about the autonomous vehicles, cars, and how whole electrification is taking place. Okay, so with this, let's get started. A quick about me, because many of the folks might not know about when I say Noida. Everyone knows about Delhi. So Noida is right on the right of this Delhi in Uttar Pradesh, and I stay here in Gurugram, which is left of the Delhi in Haryana. So I cross 3 states to get to my job, and I want my mobility to be as easy, as comfortable as possible, as green as possible. I'm into a few things, numismatics. Lately, I'm fond of traveling and reading. So if you happen to be, any of us, if you share the common thoughts, we have more reasons to talk. And I'm here for the next 3 days all together. The conference, we can speak more. Well, about this picture, don't try to even compare. I really paid well to this photographer. So this was done almost 15 years back while I got married, and that was the only time I had a paid picture. But this has become a thumbnail for all the all the communities I participate, all the talks I deliver. I'm into few of these technical activities, and if you happen to be associated from with any of them, we have more reasons to talk. Maybe during the tea break or after the talk today, and probably during the conference around. I have a quick video to play to give you a glimpse of what all innovations are happening around automotive, and probably we'll see as we talk in next 80-90 minutes how those are getting realized by all the technical stuff. So let me try to play this. So how was it? So next 60, 70, 80 minutes, I'll try to introduce you all the innovations are happening around this whole autonomous vehicle and mobility era, and then Costas will deep dive into the radar part of it. Okay, so let's move forward. I was strictly told by the technical program team of the conference that no marketing pitch, but I was strictly told by my corporates that do brand NXP. Okay, great. So I'll take a midway. We'll quickly introduce a little thoughts about NXP. So at NXP, we strongly believe in secure connections for a smarter world. Our digital NS world is evolving to anticipate and automate. And then this automation is not only limited to automobiles. This automation can be limited to your Alexa, your smartwatch, or whatnot. At NXP, we are into many verticals from automotive to industrial to mobile to smart homes, smart cities, communication infrastructure. We have a combined experience of 60 years, presence in 30 countries, about 31,000 employees. Headquarters at Netherlands, Eindhoven, from where Costa comes. A huge focus of innovation at NXP. We have about 9,500 patents, and as we speak, this number keeps on growing. And within that 31,000 employees, we have 11K only and only engineers, because we still have people from fab and different other domains working at NXP. Why automotive? And why automotive session from NXP? This slide speaks. So we are, global leaders in many of these segments, as you see on the slide here. And it's not a single site or single group or single business unit who works in this domain. We have as I said, diverse diverse workforce across 30 countries who makes realize this whole dream. So with this, let's get to our agenda. Our world is changing, and how it is changing, you can make out from these pictures. If you see top right, that was the favorite thing we did in last 2 years: day, night, morning, evening. Inside your bedroom, inside your blankets, even to inside your washrooms. So the average online time was maximum in last 2 years during the COVID time. And I give big thanks to COVID, because COVID really fast tracked our digital evolution. Okay. The digitalization which is undertaken in last 2 years during the COVID time, we might have taken almost a decade to reach to that level of digitalization. But thanks to COVID, that could happen. There are many other automations happening, like your smartwatches for your health monitoring things. We learned how to be 6 feet apart, but still do taper on time. Many other communication things. These robots, these are quite a common scene, at least back in Austin, where we had a headquarter of Legacy Freescale, and my last visit, even I could experience that. By the way, this is not the picture I clicked, but I saw the similar robots who go out and do the delivery. Okay, it's again a I would say side leg of autonomous, wherein you don't need not to have a delivery person go and ring your bell and deliver the things. But this whole evolution has really put us on spot that how technology can be beneficial without a human taking decisions, or human uh, taking good or bad, or ugly decisions in general. So and that gives a lot of another topic which is related to ethics, which is picking up quite a good momentum all across the globe, because this is one of the typical question being asked in many of the forums, and you might have heard about it. Like, if you're on a road, and if there's a young gentleman and there's a age person, there's a pregnant lady, okay, whom to hit and why. And probably we added some more dimensions, like there's a cow and there's a buffalo in Indian scenario on the road, whom to hit and why. And then I asked which state this is, because if we are in Uttar Pradesh, we know whom to save. Okay, I'm just talking about the cow and buffalo. So that brings in another dimensions of ethics. We are not going to talk about this, but that's again one of the domains which few of you might be interested in. So as the world is changing, from offline to online, from physical to virtual, so do our mobility is changing. Any guesses? What is this on the right?
First car.
First car.
First
By how many decades back?
1800s. 1800s.
Yes. 1886, if I'm not wrong. That's when this was patented, and this three-wheeler car went on a public drive. And here we are, 135, 136 years later. That's how the future cars are looking like. I think you are trying to look for that big engine that is shrinking day by day. So as our technology is shrinking, so do our engines. And I'll show you this picture again towards the end of our discussion today. And what is making this shift in automotive mobility? There are a lot of things here. I don't want to read through all of them, but have a look on the bottom here. Average vehicle today is having about 1,000 semiconductors sitting inside it, and a bill of material about $640. It's not that all 640 comes to NXP, being shared by all of our ecosystem partners. But see at the picture below, by 2030, which is just a couple of lakhs ahead, we'll have about 1,200 semiconductors coming in, and about $1,000 per car, is going to spend only on the semiconductors. And if we talk about our US particular scenario, this number goes to 1200 because the safety security resolutions are more, because India mein sab chalta hai. We manage things. We wait for that car accident to happen in Mumbai, Pune highways to make the rear seat belt compulsory for us. But typically, this shows, the level of semicon which gets into a typical car today, and that's why, we'll focus from business perspective on automotive. Let's see the global mega trends in automotive. I have categorized majorly in three parts. I'm sure there are 10 or 15 or 20 many other aspects, but we are going to talk about these three in today's talk. We'll focus on autonomous, zero road accidents. 90% of accidents are due to human errors. Electrification, we really want to be zero emission. Increasing global regulations. There are a lot of talks already, being done across the globe how to be carbon neutral by which year, or across the globe or across India, we even pledged some numbers. But how do we get that electrification? Because the moment you take this whole carbon out, then you can only reach to these carbon zero numbers. The third thing which we are going to focus about is connectivity. Zero time wasted. Intelligent transport systems, new opportunities for infotainment, powertrain, and whatnot. And within that connectivity, I'll leave the radar part to be, covered by Costas. Okay, so with this, let's focus on autonomy. And many of these things, when we discuss, are not only applicable to a car. It could be autonomy for a robo. It could be autonomy of something which you see in day to day in your life at your home or at your office or while you commute. Again, some figures here. About 1.3 million road traffic deaths occur every year all across the globe. And let's try to understand, if you're running, if you're driving at a speed of 35 kilometers per hour, and unfortunate if you get hit by a car, like 9 out of 10, humans, they survive. If you increase the speed to say 50, the number goes little bad, 5 out of 10 are gone. And if you make it like our expressways in India, where typically it is more than 70 is permissible limit, only 1 out of 10 pedestrians survives. So we want zero time wasted, but again, zero fatalities on the road. And as you see, 90% of the deaths are due to humans. And so if there is a robot sitting, probably we expect it to do a better job. But, coming across Gochibowli Junction with the autonomous car is a dream. I assume with the generation sitting in this room, probably we might see that getting realized. Okay. And this is something, which is being, these are not my figures being picked up by the standard sources. So let's try to understand the automation level. So first is no automation, all mechanical, all done by a human, a smart fellow like you or me driving it. Excuse me. Thank you. Next comes the driver assisted. So there's a assistant system in place where whole longitude, latitude, diseases are being assisted by that particular system to this driver. The next level comes up a partial automation, where your automobile can get into automotive way, autonomous mode, but if required, there is a human still sitting inside the car who can, take a control. So it's like the cruise modes typically we see in many of our vehicles these days in India. Conditional is something, wherein there's still a human sitting inside the car. The car is able to, run at its own. But if there is a scenario which is being created, which we assume, difficult to tackle in the given situation, it gives enough time for the human intervention, the human sitting on the car to, take control of this and move forward. Sorry for being ignorant about that side. Okay, I'm asked to stand here. I don't know who's watching on Zoom. I'm not that smart to be recorded. That's fine. You'll record audio. Okay. So the next one comes up high automation, which is almost we want this guy to getting out of our vehicles. And the top one is where we call it level 5, which is fully automation, where we don't expect even a human to sit as a driver. Certainly there would be passengers in the vehicle. And what I feel, this full automation probably we'll see in our lifetime. As of now, we are paying to our buses, to commute from place A to place B. I feel I don't know how much right I am. In future, you need not to pay to that travel ticket. So you might be wondering then how they are gonna make money. Any guesses?
And how you go and how you get in, the moment you get in, get down, I think it can be charged to your wallet or something.
Oh, okay, that RF tags or an NFC. Okay, no. So what I was trying to make out is probably I feel there would be a McDonald's or KFC inside your car because no one is going to drive. You just need to, it's a way to commute. You go and buy things, and that's how they'll make money for all the battery or charging they are doing for the car. So that's how I see the full automation once we have it on the roads for change our mobility. So 0 to 2 human drivers, level 3 to 5 automated driving system performs entire dynamic driving tasks and monitor whole of the environment. I'll just touch upon modeling and planning part of this automation, though there are n number of other concepts involved. Just want to give you a little glimpse of. So modeling is something where a monitor and modeling like something which gets monitored and it's being modeled, and sensors and telemetrics mix of both takes care of this modeling part. There's a fusion architecture. There's not a I would say single recipe. It's a sandwich architecture which we typically use in any of these modeling parts. Interoperability or the heterogeneous solutions. So as I said, the moment this car is driving, there is a signage in here. There might be let's assume there one typical scenario we talk about is there's a lady on a wheelchair. There could be a gentleman as well, and she's trying to get hold of a duck, and she's just doing a rolling things on the road just next to her house. So if there's an autonomous vehicle coming in, this guy don't know whether she's going straight or she's coming back because she's just rolling around. Let's talk about one more typical Indian scenario. There's a big poly bag in the air. Now this autonomous vehicle needs to identify whether there's a human or not. If I hit that particular object, whether that's going to harm the car or the passenger sitting inside it, or it might harm that could be a bird. Okay, so we need to really understand, make the coordinates and see what it is and what it is not. There's a life or there's a no life in that particular object. Okay, and same goes for our signals or directions or many different I would say guidance which is typically expected to be there on the roadside, but at times being hidden by the trees. I don't know how do we identify that there's a signage out across that trees, etc. Coming to planning side, behavior policies and actuations. So when I say policies, those are the things which when we talk about AI ethics and many other stuff where we assume it's not only the autonomous vehicle which needs to take a call, but there is a lot of decision making goes in the background, which helps or assist this whole vehicle to proceed further. And now this decision making is not done by a human. It is something on the fly. Instantly someone needs to take a decision, and it's like real time. There are cameras which are giving feed to this central box. The central box needs to receive feed from all these 6-8 cameras, process it, draw a conclusion out of it, and take a corrective action on that conclusion. And this has to happen in real time. Okay, it should not be a typical GPRS kind of scenario where you see streaming, and that video doesn't turn up. So this needs to be done before a blink of eye. That's fast this processing is. and it has to be accurate enough because there's a life behind the wheels. Let me give you another scenario. Suppose there is a hospital where 100 deliveries are happening a day. We don't think of missing a single delivery. But wherein if you buy a toy and if it doesn't work on the first day, that's perfectly fine. Okay, so that huge level of reliability goes back in automotive vehicles. A quick view of this autonomy, and if as you see in the screen, many things they come into picture. Let me start from the right, from lidars to ADAS vision stuff to automotive high performance computing, because computing I feel is the key, is the brain or the heart, because whatever you get from the real time camera, if you don't do the compute fast enough and take a right decision, you can't proceed well. V2X, anyone who don't know about V2X? Yes, ma'am. You don't know. Do you know what is V?
Vehicle.
Vehicle. So there are two terms, terminologies, V2V and V2X. V2V is vehicle to vehicle, one vehicle talking to the other vehicle. V2X, vehicle talking to some infrastructure. Okay. So in autonomous vehicle, what we presume, or like the ideal level 5 autonomous is something, if you're going straight down the line, this vehicle should understand if there is someone driving parallel to him in some other road and probably running in some speed which will intersect on a given junction. So this vehicle is talking to the other vehicle. Okay, and this vehicle is again talking to the infrastructure, that lighting system there, or it's trying to interpret whether it's red, orange, or a green light. It is reading the signage and trying to make out whether 70 kilometer per hour or say 80 or 60 kilometer per hour is the permissible speed limit. Okay, whether it is allowed to overtake or not, whether the slip road left or left turn in India, right in other places, is permissible or not. Radar on the top left, I'll not touch upon. Costas will cover up this, but these are the top level autonomous features, or I would say utilities, which we expect in a typical vehicle. And for my dear student friends here, you need not to be expert in everything. If you don't know V2V or V2X, is perfectly fine. But if you build up your attitude and aptitude, that you're open to all these ideas or learnings, is something which we typically look for a new hire student. Okay, so that's just what is my general perception, that for me, I did that about 25 years back. But for my fellow students here, if you're a bachelor student, probably you did a mistake 3 to 4 years back when you signed up for an engineering course, because it's a knowledge based industry. You need to continuously improve on. I was never knowing V2V, V2X when I was doing my studies. Unfortunately, in my curriculum, this VHDL Verilog was not part of curriculum even. So it's a knowledge industry. If you have the right attitude and aptitude, you learn and you develop and grow up. So don't feel bad if you don't know V or V2X. But I really appreciate that you asked this, because if you are shy of, you'll again miss the opportunity to learn. Quickly on a few other things. This is something which you would see in Costa's presentation as well, and we discussed, but he still was kind enough. Preet, you go ahead and show it. I'll explain in detail during his time. So if you see this particular vehicle as of today, it is covering few of the aspects, but it has to go range extended in many other things. So if you see there are different views. It's like a front view, front corner, rear corner. So if you in typical Indian cars today, we have seen there's 360 view which has started coming. It's not only the front view or a rear view which you need to take up. And now all these views, every single roll of wheel, you need to analyze your situation, what's happening or what could happen. Okay, because I was trying to explain to Costas, an Indian the bigger vehicle or bigger, infrastructure takes the precedence. So if pedestrian is on the roll and there's a bike coming in, the bike takes precedence. But if there's a car falling up, the car takes the precedence over the bike, and if there's a big tanker coming in, he's the king. Okay. So an autonomous vehicle, this guy needs to understand which shape of this particular vehicle coming in, and how to take a right decision at the right time. Quickly about vision. So this picture is trying to show you a few of the views. So if you see this particular car going in here, it is just focusing on the not on the front view. But if you see, this is if there are two vehicles just adjacent to each other, you need to know what is on my left, which speed it is coming, which angle this guy is trying to tilt on. Okay, whether it will get to a huge vicinity wherein these two can collide or not. There are different driver monitors, and their perceptions we create. Okay, the how this whole automation thought process of thinking or decision making happens. We need to at time create a perception. Okay, I'm moving in here. There's something on my left. There are two vehicles. Then there are some pedestrian going in out here. Okay, so we need to see where exactly is that object, and at what angle this object is moving, and at what speed it is moving. And if this guy keeps on moving with the same angle, with the same speed in the same direction, whether our vehicle is going to collide with this other object or other human or not. And this all has to be done in real time. We don't get 3 hours to attempt the question, and you need to take a decision. Reason again today for today and tomorrow. There are many things which comes into play, which is surround view. Vision for 3D segments, and we really want to keep on extending it today, tomorrow, and probably in future we'll have a slide day after tomorrow, a week later, a month later, a year later, what all we can do. And certainly Costa still today knows what we are going to do as an organization 10 years down the line. If you can bribe him, probably he might care. Quickly, rising computing and safety requirements. So what's happening as we advance through this whole autonomous? Yes, sir. Thanks for the first question. I'm happy.
Cameras and radar both, right? Why not just cameras?
So look, thank you. Thanks. This is a really good question. So it's not only camera, it's not only radar, it's not only lidar. It is a mix of all. Okay. So yeah. So it is a mix of all. Now let's assume that please be seated. So this is something different solutions, they work for different segments. Okay. And second, different suppliers, or I would say, okay, let me try to make you understand. We as a NXP, we are doing something which is inside a tiny chip. Okay. So we designed the chip. We have our own fabs to manufacture them, or we have our partners who manufacture it. Now this particular chip is sent to next level of OEM. Okay. Please be loud.
Original equipment manufacturer.
Okay. So now this OEM could be, with all due respect to all the OEMs we work for, but I'll give you a couple of names. That doesn't mean these are the only OEMs we work for. That doesn't mean these are the favorite ones of our organization or mine. But just for example, like Bosch, Denso, Conti. Okay. So these are the guys who will pick up our NXP chips, and they'll, create a whole solution around it. Now these whole chip along with this surrounding components or boards, that is now being shipped to say, Mercedes or Audi or BMW or Jaguar or Maruti or whatnot brands. And now these guys, they pick up this part and they pick up other 10 different components, steering, wheels, chassis, etc., etc. They stitch them together and then they sell you the final car. Okay. So in this whole value chain from, the chip supplier like us, from the next level of OEMs, we have different tier of OEMs, and finally to the end car manufacturer who's giving you the final product. This whole value chain, they sit together and they decide, what solution we want to give. So if you go to a car, I was trying to book a car recently, So there are different variants, So they said, okay, this has a 360 view. If you go to a variant down, you will still get a front and back view, but you'll not get the whole 360 view. Okay. So based on what features you want to put in, how many dollars you want to spend on, you can pick up what kind of accuracy or precision you want. So it's not that you can only use camera or you can only use radar or you can only use lidar, because each of these have some goods and bads. Okay. It might be possible that one solution might be a mix of all three, and they'll say that if I'm within this particular scenario or this particular range I'm traveling, okay, I'll probably end up using this and this, mix of camera and radar. Okay. But in particular scenario where there's a huge fog, etc., I might end up using, third means of detection or calculation.
Given that a lot of times people tend to take inspiration from nature, and in nature our eyes are the best sensors. Don't you think cameras should be the only way forward?
No, so cameras are good. I respect all our senses, five senses. But again, there's the concept of line of sight. Okay. How far you can see sitting here? How many kilometers you can foresee? And with nature, we have some of our animals and animals who can do the 360 rotation of their eyes. Unfortunately, we can't. Okay. So there is a limitation to it. Okay. As a suppose, if you want to create a small autonomous vehicle and which can only run in this room, probably camera would be a thing. But then when you need to detect a object, how far it is, with what speed it is coming in, etc., probably you'll need something else to help you. And maybe Costas might be covering as a part of his radar things this way. But thanks for asking this.
In dark environments, it will give.
In dark environment, suppose you are in Delhi, minus 2.5 degree. I had 4 layers on me when I bought the plane, and here I'm just wearing this little shirt. Okay, so we have seen a particular case. I'll not name the company. I'm not saying this is example of NXP. This is example of some again chip design company, wherein they sold of lot many vehicles all across, and it was working perfectly fine until one fine year someone complained that the car is not getting started in morning, and post noon it's better because sun is there. So for that particular condition, that temperature was playing more role. Okay. And with a diverse our geography, again coming back to India, so when you go to Goa, the fans are on. If you are in Delhi, you have 4 layers. There is somewhere dense fog, and at times if it is raining, thunderstorms are coming in. If you go to back deep in places like Jaisalmer, the temperature hits like inside a closed car. If a car is parked, it might go about 60 degrees or something. Okay, so there are a lot many weather conditions, etc., which account today can happen. Because if I'm doing let's say my solution, I can't say, well, this will work very good in Hyderabad because the temperature will never go to 2.5 degrees Celsius. But if you get transferred and join us in NXP Noida, or gets transferred from NXP Hyderabad to Noida, so you need to buy another car because it's only meant for Hyderabad weather. That's not practical. Okay. So these are the typical things which one need to take care of whenever we are doing a solution. And for automotive grade vehicles, the requirements are very stringent. If as I was giving this example of a toy car, if it is not working, it's not working. But if you are putting something in an automotive vehicle, it's not a iPhone you keep on changing every year. If you buy a car, typically you end up living with it for a decade. Okay, again, let me give you very funny example, I would call. So what is typical Indian style of using a cloth? Costas, please pay attention. So we buy a new shirt. My wife gifted me this one. So this was, I'm honestly speaking, I wore this first time in October, I was in Kerala, and she really insisted, this time you at least wear this off, So it was since May, this was just roaming around in my wardrobe. Finally, it got a chance to I wear this and I use it, for few of my public appearance. And probably after a few of those, I'll start wearing it to maybe some weddings, etc. And gradually, I'll start wearing to when I'll go to my office regularly. Gradually, the time would come, I'll say, okay, I can only wear it inside my home. Then a time would come, I'll say, okay, this is good enough to be worn in winters because there's a pullover on it, it can still last. And finally, a day would come, I'll say, okay, Holi me, I can wear this one. Holi is the festival of colors, even if it gets, some strange here, I'm fine. But still, it's not end of life. Picture abhi baki hai. So post that. So with all due respect to all of us, we are very good at giving away to the needy guys, but we give them up when Holi is past. We'll end up probably I'll give it to the person who's cleaning my car daily morning. So he might wear it for couple of years or something, and post that he'll start clearing the car. But still, it will live for a few more years because initially he or she would only use it to clean your glasses, etc. And at the end, this will get to where they will clean mud off all the wheel covers, etc. we have. So that's a typical life of a shirt in Indian context. Because it took me May, June, July, August, September, October, 6 months from wardrobe to me first time wearing it. So that's the typical life, okay? And for a car, if I buy, I want my grandson to use it. But since it's a car, there's a whole lot of reliability associated with it. I really want it to work every time. I don't want to miss a single break because there's a life inside the vehicle and there's a life outside the vehicle. Great. Yes, sir.
How do you deal with dust settling down on your car?
Dust on the car?
So many sensors
Certainly.
that might get covered with the
Certainly. So we are yet to develop masks. Okay, we can. So me and Kostas, when we went to Charminar yesterday evening, so we were realizing we missed to wear the mask. Probably that would have helped him. He had a bad throat. So similarly for all these kind of sensors, there's a lot of testing which goes in the background, and we typically do in real time scenarios, or we try to mimic it. Because I got a similar question by one of this curious BTech third year student in one of the forums. He said, "Sir, you do aging simulation, you manufacture a chip and keep it for 15 years." So we don't do that, but we simulate that environment. So similarly for all these sensors, they can work with some level of dust. Okay, ultimately, if you put a huge mud thing, which knowingly many of the truck drivers do on their number plates, is a separate scenario. But otherwise, they are based on what kind of sensors they are, and probably Costas would cover in part of the radar, to what level that can hamper your stuff. But what we do is, and we were talking about this when we were talking about level of autonomous, that if we get to some scenario like suppose some of those sensor is not working, probably on the way there's some mud or something else due to environment conditioner, unknowingly something happens, the vehicle should be smart enough to detect there is something wrong. Okay, and it should save state everything before exiting that loop and alert the driver on the vehicle, or in terms of our autonomous vehicle, our infrastructure, to get the vehicle to a safe state. Okay, so it is something. The moment you realize there is a fault in the system, it should get to a it should close all the loops and gracefully exit the whole of the system or loop and get to a safe state where the vehicle and the folks sitting inside that are safely parked. So this gives me another example. Sorry for these all funny things. So this is in context to one of the jokes I heard back in Chandigarh. I'm born part of Chandigarh. In context to little, this was told to me by one of my Punjabi friends, and he said like there was a fellow like me. He was traveling in a bus, and the co-passenger realized that he has purchased 2 pair of tickets for the same route. And this co-passenger was very curious, and he said, "You kept one ticket here in the pocket and the other one somewhere else. Why is it so?" He said, "What if someone comes and somehow steals my this particular ticket, or if it is by mistake I leave it on the somewhere on the seat, then I have a backup here, which is safe." And this guy said, "Okay, what happens if your purse is again gone, your wallet is gone?" He said, "I have this bus pass that will save me." So there's a backup of a backup when we talk about an autonomous vehicle. Okay. So if one of the ADC is not working, I have a backup ADC. Don't ask me what if the backup ADC is not working. I can't create another one. Again, I need to take a trade-off. And there are different, criteria or regulation which governs all these safety or security aspects. So there's a functional safety we'll cover a little bit. ISO 26262 for automobile, vehicles. And similarly, there are standards for healthcare and many other applications. So how it goes is that they mimic, they put in a criteria that at least if this fails, this should act. And supposedly now we know A is already down, B would come and within no time would take over. At the same time, now the system would alert the driver or the infrastructure that A is gone and B is in place, but I don't have a C to back up B. Okay. So sorry for this long answers to this short question. So we do plan those backups, but if in case something goes wrong, there should be a safe setting option. How many? Have time till? Okay. Okay, so I need to run a little fast, but quickly here this particular slide, rising computing and safety requirements. Huge focus on computing. So there are different things. If you see, the way whole computing things going on and safety taking over, be it a automated driving or a co-pilot mode or a collision things or self-parking, as you might have seen in the picture. And I think we have cars in India who can do self-park now. Lane keeping, which we really don't know by heart. Okay, but as an autonomous vehicle, we really want these vehicles to understand, which lane to keep on. Collision warning, sign views, as you might have seen in the video, there was some signage being, being monitored by the car. There was a collision on the road, the car took a diversion. So the car should know if A fails, there is a B route or a C route, etc. V2X, yes, sir.
See, nowadays, world moving towards the green energy. So many of industry manufacturing the electric cars, but in that thermal runaway is the major issue. So for that, any sensor is available for detect the heat and then give the signal to work. Don't drive the car. Stop that because already this circuitry part is the fitting and like that.
Certainly, there are many such options available. I know there were a lot many fire incidents. Costas, for your knowledge, in last 1 year we have seen many EVs getting burned out, and many of them were two-wheelers. Okay, I can't comment on the reason. Please take your seat. Thank you. Thanks for this question. So there are temperature monitors sitting inside our chip. First of all, because the chip may again get heat up. Okay, and similarly, there are temperature monitor for the other big infrastructure inside the vehicle. In our typical car, if you see the dashboard, we have a cool and heat thing showing up there. So those are the alarms, and probably now for autonomous vehicle, it is something it needs to trigger alarm in time. I'm sure for all of our chips that is already being there. There are temperature monitors. and they don't tell us when it's about to burn. They should give a well advanced warning in time that you can save state. If is a passenger in the vehicle, they get enough time to evacuate the vehicle, etc. There are many such options, but that doesn't mean it solves all of the problems, because the moment battery comes into picture, there's a lot of chemistry which gets involved. Okay, it's not only the electric, but you need to see how to find it out. But at the same time, there are many temperature monitors in place. Yes, sir.
I have a question little linked to that.
Mhm.
That is, considering we want to move to the full mobility, that's our wish. I want to understand why is it taking us a little bit more time than this wish is since many years, right? Uh, so linked to that, if we divide the total, system into three parts, we require the hardware, then we require software, and in hardware, if we break down, then we require sensors, actuators coming from the device physics point of view, let's say. And then there is a thing coming from digital and analog design, chip and system level perspective. So if I consider a autonomous car, how can we divide how much part of it is software, let's say, dependent, and how much is this delay based on hardware?
So first question, difficult to answer for me, why it is taking longer to get to automation level 5, because everything takes its own pace, and it's not, we do have autonomous vehicles in place, partial automation, automated and fully automated as well. Coming to, difficult for me to answer, how many more years we need. We still have, POC, proof of concept, they are real-time examples. But how soon it's going to be in every home would determine by many factors. One is cost. Because if you see IoT, we talk a lot about IoT in last 10 years. I don't know, somehow this has become a buzzword. But to me, 1967, I think, was the first time around when ATM was there installed in UK, where, that was the first IoT example, I call it. But why it became reality today? Because data is cheap. Okay. Because one of the biggest thing for IoT is connectivity. Okay. I remember back in 2000, we used to pay 12 rupees per minute to answer a call. Unwanted number, I never used to pick up. I'll not spend 12 rupees to speaking to unwanted number. Okay. So it is not only the technical solution which advanced it is the whole ecosystem. And why we have so many IoT and Fitbits now? Because it is quite cheap. It's quite affordable now. Okay. So it is the whole ecosystem has to run together, and I'll not give a credit to a single player here, but why data is cheap in India. Okay, the one organization who made the history. Okay, so it's not only a single thing which drives. There are POCs. I happen to share a flight with our respected Minister Nitin Gadkari. I was on a flight from NIT Nagpur. I was coming back to Delhi, and we happened to be on the same flight. And I just curiously went to him and asked him a couple of questions. He was very clear in his view. Autonomous vehicle, no, in India. Okay. So I said, well, we are the world leader in automotive semiconductors, but there are many equations to it. It's not only the technology which gives answer. So I think these two would help you to understand that IoT picked up because data has become quite a cheap and affordable in India. We missed the landline era of telecommunication in India. We were never able to connect the last mile connectivity to all the remote regions of India, but thanks to the cheap data, we could do that. There was a question here. Yes, sir.
So, but general automotive was always slow, right? In the sense, CAN to CAN FD took, I think, about 12 years or something before they adopted you CAN FD instead of CAN. So, in general, why is automotive slow in adopting to a new technology? Not just this autonomous thing, but in general also. I mean, CAN FD has nothing to do with autonomy as such. Right? It's still take a while between CAN and CAN FD as well.
Okay, so this is my perspective. Don't quote me. This is NXP's perspective. Let me make this clear, loud and clear. So I feel we are doing at NXP we are doing the first 5 nanometer automotive grade chip. Okay, and I was part of that program. I have moved to other program now. So 5 nanometer chips are available in many other solutions. Okay. If you're trying to call a number, it's not working, it's fine. You know what example I'm trying to give. But in automotive, I can't do that. Okay. So, it's like try again. And once you're very sure you get to this level, this grading of, chips. Okay. And same is the case for automotive. Once things are very much strongly reliable, then only those get implemented, inside the vehicle. So probably that's one of the reasons why, we don't run that fast in automotive segments. But if it is just some other application or IoT Fitbit which you're wearing, if it is not able to calculate 10 of your steps, it's still fine. Okay, that's why it's little slow. It takes huge precision, huge reliability, and we need to give you that precision and reliability of the same state and level 10 years down the line. It's not only applicable today, tomorrow, a month, or a year later. It is 10 years down the line, and that's why it takes huge certification and other things to get to automotive domain. Okay, I'm left with 28 minutes. I really need to rush now. I'll skip few of the slides in the interest of time. Here comes the EV thing. This gentleman was asking. Electrification, the green mobility. There was a summit in Glasgow last year. Many countries pledged many things, net zero, etc., etc. We as a country also pledged some numbers. I don't want to count those. I call that numbers now. But how this? Because one of the major means of this pollution is our whole mobility. Okay, and so this whole electrification, again, it has many segments. I'll start with typical combustion engines, which we have. I call it E0. The next one is mild hybrid. We have a lot of mild hybrid happening in India. Almost every other supplier is, having a mild hybrid model these days. Full hybrid, again, where there's a, your combustion engine is still inside your vehicle, but there are other means wherein you need not to plug in to charge your batteries, but your battery gets charged with, stop break kind of systems. E3 is something plug-in, wherein you need to plug in your vehicle to charge it. Okay. And you run fast. Range extended, E4 level of electric vehicle, where it's majorly the electric motor, which is, running all of your show. And the last is the pure electric, where I don't need a combustion engine. Whereas combustion engine is already out. This probably slide would tell you. But pure electric is the one where I say pure green mobility. Okay. But I give this question to all the folks who talk about green mobility. We are solving one problem to create another, because we still don't know all the batteries which we are trying to manufacture to power all these vehicles. How do we reuse or recycle those batteries? Because there's a famous big landfill next to the exit of Delhi border, which has shown in many movies, Hollywood movies even. So we are trying to create another such big, I would say, recycled, e-waste generated from batteries. But certainly carbon footprints are better. But how do we reuse? Because there are many other companies. I was talking to one of the startups recently. They are trying to optimize the battery life. They said, give me a dead battery and I'll still infuse some life in it. So quickly here, the different level of electrification. If you see, once you get to this PHEV, we call it, it is something. Yes, sir.
So how do we say that becoming more green with electrification? Because the point is we are charging our batteries only, right? Still, the power is still coming from some power stations, which may be running on coal.
Which may be running on coal. It might not be running on coal. Okay, I'll come to this. Okay, thanks for giving me the answer. Okay.
High percentage of
certainly. If you see the combustion engine, certainly the whole lot of I would say pollution which is being generated as compared to electric vehicle is less. But certainly to get that electricity, how do we produce electricity? Is it coming from a nuclear plant, which is hardly doing any kind of effect over environment? typically, or is it coming from a correlated thing, or through water you're generating electricity is a separate part. But as I said, we are solving one problem and creating other, and that's how we keep on evolving. Okay, but the moment you call it green mobility, it is a mobility in which the final product, a car or vehicle, is not polluting your environment. But now you will say that you're generating plastic and metals to manufacture car, and that's polluting. Certainly, yes. But the end product is not, generating pollution for you. And if you see electric traction, so the traction keeps on, the watts keep on, increasing, getting to 80 kilowatts range for the pure electric, whereas it was just 10 kV for a mild hybrid car. So these are the different segment of electrifications. Let me jump on connectivity, where I really want to spend a little more time. So as like electrification and autonomous, there's a different level of connectivity, we call it. First is no connectivity. Our typical Fiat car, you have one parked in your Chomula Palace. I went there, so they still had a Fiat there parked in a green color. And then some analog radio, more connectivity, with 2G, 3G, amplitude modulation, frequency modulation. Digital radio, 4G. We already have 5G in India. Then the next level of connectivity with LTE, advanced, etc. And finally, a fully connected car, which is which can talk to different devices or different other infrastructure or different other vehicles. Okay, so I'll talk about the different connectivities in a few of the next slide. I'll try to wrap in 10 minutes, and then we'll conclude. We'll spend next 10 minutes about the future car infrastructure. So here I just want to give some glimpse about when we talk about V2X, as she asked. So there are many means to this vehicle to interact with the infrastructure. Similarly, there are modems, 4G, 5G, and now we already started talking about 6G kind of connectivity. Broadcast reception, analog radio, digital radio, satellite radio. We are talking software defined radios. But when we talk about radio, this always reminds me this example of a Jeep being hacked many years back. So how that car was hacked, I'm sure many of you must be knowing, but for the knowledge of the other audience who might not be knowing, so this hacker, he got into the car through a radio channel. Because we never secure our AM, FM radios, So I need not to secure, there's no banking password residing inside that radio. But through this radio channel, they were able to get control of the whole vehicle. So similarly, back in 2013, there was this, there were many, many spam mails were getting generated. And one of the agencies took over and they said, okay, let's see from where this was getting generated. This was getting generated from a house. Okay. So as like we have biased minds, so we'll think of probably from some laptop this might be happening, but that was happening through a refrigerator. Because when we buy a smart refrigerator, typically we don't change its password. Okay, but if someone gets hold of your refrigerator, because your refrigerator is talking to your tab, telling him, I'm out of milk. Order, couple of more packs of milk for me. And now this tab is always connected to your laptop, etc. And laptop has your password, your pictures, whatnot. So anything in the whole chain, the weakest link is something as a smart hacker is looking for. So to me, when I talk about security, it is either secure or not secure. There's nothing like partial secure. Okay, let's move forward. Similarly, for car access security, we have I have some material on safety and security. I think I'll eat up 5 minutes in your tea break as well. I need to run fast to cover those topics. I quickly want to really talk about UWB, ultra wideband, getting a lot of traction as an organization. It is accurate positioning of information of objects in real time. It is the next slide would tell you how precise it could be. As you can see, this guy standing here in the center, it can exactly different objects and exactly position it. It is typically being used in your driverless keys, okay, wherein it can make out how many, what distance it is and what angle the things are. So if you see, the accuracy is in centimeter distance, plus minus 10 centimeter, it can detect where the UWB object is found. Plus minus 3 degree of angle, that is the huge accuracy. Robustness is strong to multipath environment, 2 nanosecond radio pulses. Range is 100 meters of range under line of sight, which we were talking about. Protected through the cryptic things, real time, no latency at all. So this is one of the solutions which is getting a lot of traction. I've seen few of the groups and even startups working their solutions around it. And this is not only applicable to autonomous vehicles. This carless entry is one of the applications, but this can be used in many other different applications within your home, within your workspace, etc. Let me skip this one quickly. We'll talk about security in other slides. And there are many use cases for UWB. It could be, honor pairing. You can pair your car. The car can be paired through your smart device, mobile or laptops or a tablet. Vehicle access and engine start. So, if someone wants to ask your car, earlier days we used to say, oh, well, my key is somewhere, I can't lend you my car. Now you can, through your mobile, you can send your key. Okay. You can share your digital keys probably with your family member. Any of them is having the digital key, they can get access to. Termination and suspension, you can terminate or suspend the access. Suppose, I think this is a feature in Indian cars these days, wherein you can put in the radius within that radius. If the car goes out of radius, you can, terminate that car. You can bring it to a halt, etc. So those are the applications. Similarly, secure car access. This is just a quick, comparison between a classic key, a smart key, and the high-end smart key, which we are talking about with UWB. So if you see, it has added up one or the other feature. NFC is similar to KFC. So that's the easiest way to remember it. So it's near field communication. That's again one of the pioneer solution for us, and I take a lot of proud. Lot many applications in India. If you happen to use a metro card, I don't want to quote number, but someone told me we were like 70% of that market is something with us. Unofficially, on my personal behalf, not of NXP's behalf, let me correct. Okay, so that all is the near field communication applications. You might have seen that smart ring. This lady and this guy, they exchange their credentials using it. That all is NFC. All the tap and go are NFCs. Safety and security. I'm very fond of this topic. And when I say safe, it should be safe by concept. Okay, because traditionally, what was happening, we were creating a solution. When the solution is created, that time we realize, oh well, I need to safeguard it. Okay, and then we used to try to put a last layer of porting, etc. I strongly feel safety should be by concept. The day you are defining your product, the day you are conceptualizing your product, be it a car or whatsoever it is, the safety should be part of it. Okay, so it's not that you constructed a house and at the end you created a big metal gate in the front and you said, like, I have a strong gate, I can safeguard my house. What we are talking about is someone who got into that jumped the metal gate and got into the main access. Then again, we need to show, even if someone is able to get into my chip, within that chip, it should not get into my critical functionality. Okay, so that level of safety is something we talk about. So, and to go in this safety, as I was talking, Automotive ISO 26262, it goes lot many safety standards. Okay, and we follow it by heart at NXP. So, automotive level products, everyone has to undergo some trainings and certification. Only then you can work on. Similarly, there's a IEC 61508, and there are many more different standards which one needs to follow on, and they have their own governing ways that there should be a backup of backup. Okay. Safety and security by design, there are three things which typically I feel we need to focus on. One is functional safety, we call it FUSA as well, FUSA. And every automotive domain player, it need not to be only chip manufacturer, it is all the OEMs. They need to they are part of this whole FUSA definition. Security, and then component reliability and robustness, because what is working today, I want the same level of perfection, same level of precision. When we talk about UWB and we say that 10 centimeter, it has to be 10 centimeter 10 year down the line, or whatever is the life of the vehicle. Quickly, again, there's a new term being added up. I think you already know functional safety and security, most of you here. Safety on, intended functionality, SOTIF. And there are many different, yes, sir.
What is the highest DC coverage you have for your chips or IP?
Highest
DC coverage.
Well, now it depends upon what kind of application I'm using this particular chip for. That would define. I can't make it. I can't speak in public. What exactly it is, but certainly that is very readily governed by this whole ISO 262 standards and the other IC standards. Similarly, within the car, as we were talking, if there is a radio in the car, it would have a different level of safety and security. But wherein if it comes to a ABS, okay, automatic braking system, or I would say your this airbag system, etc., that comes to a different level of coverages as applicable. But it's not that one standard would fit in every semicon which is sitting inside your car.
Do you use your own tools or a third party tool for post analysis?
To all my EDA friends sitting in this room, so we do use our own tools. We do use the industry standard tools. We have our own simulators, which are industry standards, which are being benchmarked. That doesn't mean we are not using any, all the standard EDA vendor tools, but it's a mix of both. Like we have our own fabs and we have our, vendor fabs as well.
Is it standardized?
As I said, I have one of our simulator, which is industry standards. We benchmarked it as in one of those practices, and there were people who wanted to license our tools. Okay, let's move forward. I'm gonna skip few of the slides. Okay, cybersecurity is something I would take a quick run because I want to spend some time on the vehicle architecture and conclusion. Okay, yeah. So this is another slide which talks about the different level of safety or security standards. So there are different ASIL level. I'll not name what it is. Okay, if you want to be in automotive domain, you should know this. And there are different grades. If you see A, B, or C or D, which level of standards they are, and they are for different level of applications, different standards gets in. Okay, so when we plan a chip, we plan that out which standard it should lie. It should be SLA or B or C or D compliant or not. And if you see there are different applications for powertrain, for electrification, for safety, for body control, for chassis, for vehicle networking, etc. And it shows this should be compliant to what SL level. Again, there are different examples of a safety event and how what kind of safety standard they should live on. If you see SLB, SLC, or SLD for power steering, etc. I'm gonna skip few slides. I'm left with 9 minutes. Am I right, Mr. Radhe? So let's talk about architecture of a car for the future. I really wanted to spend some time on this. So if you see typically vehicle architecture, how that's transforming. This is today. Don't read it Fiat. It is flat. Okay. So today's architecture is typically a flat car. Whereas if we talk about a flat architecture, it is something which is all across, okay, which doesn't have multiple layer of computing or processing available. So it's like unit of mobility, which we or not only we everyone is talking about, but how we perceive is a logical restructuring. Okay, so the car is now getting smarter. So the typical definition of a smart device in a layman language, I would say the moment you have a connectivity, it becomes smart. So your typical keypad phones, 3310, if you can recall the snake game, the moment they got connectivity through this all apps, etc., sensors, they become smartphone. Similarly, your television became smart television, your oven became smart oven, your fridge became a smart fridge, and similarly, a car became a smart, car. So here we talk about different domains. I don't know how well you can read it. So this is a domain controller, other domain controller, next domain controller, and there are different domains. The car is being segmented, and service-oriented gateways, being connected for all of these domains. But how we foresee as we move forward, like there's one domain for connectivity, one for entertainment, one for body comfort, powertrain, ADAS, etc. So how we foresee is something which is a physical restructuring, creating different zones. Okay, so this is how we foresee the future cards would probably look like. There'll be so there'll be different zonal gateways sitting in the car, and then there's a central brain or processing unit which is talking to all these zonal gateways and taking a final decision. Okay, so from flat architecture, we first created different domains. There was a controller for each of the domains, but now I want to bring in a powerhouse here. Okay, but now the question comes up: the powerhouse has to be really, I would say, a strong compute system which can real time speak to all these guys. Does the compute go back to these folks to take a corrective action? And in a fraction of seconds, before you blink your eye, the action should take place. Let me skip, because domains I don't want to talk about more. We already talked about zonal thing here. So different sensors in automotive, as you might have seen in the initial slide, and it is all across your car. It is not only a segment or single feature which needs to be controlled on. Well, I don't call it a marketing slide. This is one of our product families which has all these solutions coming in. So if you recall the slide wherein we talked about the three-wheeler to automation. So here the whole magic is sitting inside this red box. Okay. And I have one slide, probably following one or the next one, where it will make a comparison between the traditional car shit, which we are seeing, how the whole wiring things are going on, and you'll see some amazing feature. This is a very good detailed slide. I might take hours and days to explain it, but let me try to cover it up in a couple of minutes. So within connectivity, there are like different. So at NXP, we segment these things into sense, think, and act. Okay. So if you see about the sensing, it could be this connectivity through. It could be a V2V, V2X, or it could be through cellular or Wi-Fi. When we say BT, it is Bluetooth. There's a Bluetooth low power. Then NFC is near field communication, ultra wideband, smart car access, radio access. Within ADAS, there are cameras, lidar, radar, and to answer that your question, probably Kostas will cover details in radar. Coming to powertrain, vehicle dynamics, motion, pressure, speed, ultrasonic, body and comfort, temperature, light, humidity, switch panels. Huge innovation is going in the lighting domain itself now. Inside the vehicle, you might have seen those small LEDs all together, and their life is long. LED goes long time, and the industry is pretty good, and they are very low power operated. If you might have seen, most of the times we are now replacing those yellow bulbs. I don't know whether your generation has seen that, to that CFLs and now to LEDs. And someone asked me again this question. That was a PhD scholar in one of the forum, and he said that typically it is said that LED has a huge life. Okay, but he said, sir, in my home, the LED bulb I'm getting is hardly laying for a year or two. So most of the time, which I feel, again, my personal perception, the LED has that good life, but that controller is something which is malfunctioning. So that is one of the area which lighting guys are focusing on, the controller which controls the LED. So if you somehow detach that controller and bring a new one, probably that LED would still work, but it is so minute you can't. It's not the typical soldering thing which we used to do a couple of decades back, which you can do with hand. Okay, but that controller is again getting improved on. Infotainment in vehicle experience. So we want to see you state of the art infotainment. You're in an autonomous vehicle, a huge screen in front of you, enjoying your meal or having a Teams meeting, doing some circuits, etc. is something we foresee. And there's again huge investment going on in infotainment. Few of the recent models have seen even in India market, the infotainment is expanding, and it's going to replace the whole front dashboard pretty soon. Not a marketing slide, but these are the few of the areas we as an organization or in general automotive domain are focused on: the performance, safety, security. Over the air, we want to upgrade your things. Okay, if you're personally, I'm a diehard fan of iPhones. My whole family is on Apple. The moment you get a better upgrade of your iOS, the whole look and feel changes. It's the same screen, it's the same hardware, only upgrading your software, you get a new look and feel. Okay, but when you do this over the air upgrades, that is the time where a lot of bugs get into it. We have seen this, one of the nuclear plant getting compromised when it was getting serviced. Okay, so it is, you opened your locker to get it clean, and it really got cleaned. Okay, so those are the all aspects one needs to take care while you do any of such upgrades. Sense, think, connect, and act. So sense part, radar V2X. Think part, the integrated whole uniform platform using connection, using UWB and electrification. Anyways, I'll quickly talk about. I wanted to talk about is whatever solution you are developing today should be scalable. You don't want to bring your car physically back to a workshop to scale it to the latest offerings. Okay. So someone asked me this question about software. There's a huge focus getting into the software now, not only within an organization but in industry. Okay, so earlier there were chip suppliers who are giving only the hardware chip, and then they used to this OEM used to get someone else to understand the make a software or solution around it, and it was very difficult. It's like I'm trying to mild this example. It's something, your wife has cooked a recipe and you're now trying to serve it well. Okay, at least I'm very bad in kitchen. I can't do the due diligence. It's something, a solution coming from one guy, and the other person is understanding the solution and developing a software around it. And how that shift is happening in industries now, all the hardware guys, they want to have their own software. So they want to sell a package solution, not only a chip but the whole platform to the OEMs. So the software should be scalable and expandable. For secure connection for a smarter world, which has evolved at NXP, if you see, we strongly believe in that with cloud infrastructure and enabling technologies and edge-to-edge connectivity, be it a home gateway or automotive gateway or a smart city or a smart health monitor, etc., etc. These are the segments which we touched on. It's not only the automotive; it is industrial IoTs or mobile or communication infrastructures. I'm going to skip this guy, but we want everything to be aware, to be connected, to be smart, to be efficient. At the same time, it has to be safe and secure. If you are missing this, there's no point of having all those things. Okay. So just think of the safety in that perception. I was trying to give you an example that suppose someone is able to, if you are in an independent house, if someone is able to jump over the metallic gate of your house, just try to visualize, and this guy is able to enter through the main door. Still, you want the other rooms to be secured. Even if this person gets into the other room, you want your wardrobe where your locker is sitting to be secured. So that is the multi-layer of security we want. If someone is able to get access to through a radio channel of the car, I don't want him to get access to my braking system or my steering wheel. Let me skip this up, but these are the various platforms we at NXT works on, Kinetics to IMAX to Layerscape to, S32 platform where I personally contributed. I want to quickly talk about it's not only the hardware to answer your question. So the car, it runs on code about 150 million lines today. When I say it's not literally today, nowadays. Okay. And this is, increasing the complexity as higher level as safety and securities are required. So the more layer of safety and security you want to put in more layer of, even software blockages on over it. So shifting to automotive driving, understand, predict the environment, mix of AI and deterministic computing. We want very, very low latency in taking all these decisions. Levels of electrification. We really want this to be, energy reduction, route planning, again, that helps in reducing, and then mechanical replacements. The connected upgradable car, the whole look and feel should be upgradable. It's not something which I bought today. I'm going to live for next 10 years. The infotainment can be whole restructured together. Future of automotive mobility, I just want to I'll play this quick quiz for you. So let's assume you are residing in a high rise. Where is your, nameplate or number plate? It's at the entrance of your house today. Where you think this would move in future? Any guesses? Come on, quickly. I need to conclude in next 1 minute. I'm 4 minutes overdue already. My question is, if you're if you're residing inside a flat, at the entrance you have your nameplate written there. Someone would identify with that house number, 318 or whatsoever it is, the third floor, 18th house. Okay, where you think that nameplate would go in future? Cloud. Okay. So let me quickly run through. So if you want such kind of automotive vehicles, to deliver stuff to your things, that those would land in your balconies now. So you will have a RF tag in your balcony. Using that RF tag, this guy would get to know, okay, this is my destination to place your, hot pizzas or medication or groceries or whatnot.
What if I don't have one?
Sorry? What if? Don't have a balcony, but there would be, there are some things going on in smart homes. They'll have a delivery windows happening in wherein the drone would come in. It will identify this is a window I need to deliver in. There will be a secure connection, secure communication being established between the drone and the window. The window would get open. Based on the size of the packet, the window would expand and the drone would deliver it and move off. So next time you have a ground floor house, don't look for a balcony. Quickly about how this whole shift is going. Don't ask me this question that you were talking about some thousands of semiconductor. Now you're talking about 10 units. These are the processor units we are talking about. Okay, so if we are here in 2020 about 45 processors, we see that increasing 25% more. Zonal things is still evolving. Line of code used to be 4K, and we were talking about thousands of millions here. The wiring used to be this big. We want to reduce that wiring to 50%. Recall that future zonal thing, central unit we were talking about, because wire harness itself is a good weight for the vehicle, which needs to be reduced. Weight of the harness, as I was talking, that has gone up to 75 kgs now. We want to reduce it to the half because we want this central unit. We don't want many wires going in. For that instance, if you see the space shuttles which we have, their wiring goes into kilometers and kilometers. One last point here at the bottom, this is very important. Data transfer per day is going to be huge with this autonomous vehicle. Okay, and that brings up another challenge: how quickly that data can be sent. First of all, how quickly you can get the meaningful data. how, and you can't keep that whole data inside the car. That has to be transferred, purely transferred, to the infrastructure. Future of mobility, I feel the path of autonomy being refined by technology and market dynamics, because it's not only the technology which drives, it's the market which drives. Ye dil mange more, what you want as a client is something we as a component supplier would work on. Focus on focus on system scalability and flexibility. The system should be scalable enough. If I have a system, a hardware, or a car sold to you today, and 3 years down the line there's something else coming up, I should have a plug and play available for that particular car to get upgraded, and it should be flexible enough. We are talking about standard charger all across. Okay. Modular and expandable in system solution. It's like pick and choose, plug and play. I want to wear brown shoes, brown trouser, or a black attire, or I want to flip my belt. All those kind of flexible option is something I want to see inside my car. Continue to optimize technology for safe and secure domain, because certainly whatever optimization or whatever upgradation you do has to be first safe and secure, and then you talk about anything else inside the car. And that's why, to answer this gentleman's question, it takes ages for us to bring in the same kind of solution inside the automobile vehicle. With this, any last questions? Or else I'll be here during the break to answer any questions, and probably for the next 3 days during the conference as well. That's the first and the last question. And we'll break. Yeah. Yes, sir.
Electrification charging point of view. Have you tried to use solar panels to charge it?
Solar system to charge my okay. So there are a lot many nice videos which I come across, okay, wherein people want to make the whole, someone said first fix on the roof fix a solar panel. The other guy said, why don't you make the whole body of solar, and I am proposing making your walls of solar. I want the brick itself to be a solar system, not add up a solar later to it. Okay. So yeah, those are different modularities which one needs to work on. But what if you are in Delhi in the first or last week of, first month of year in January, you hardly see sun very well. Okay. So that could be one of the add-on capabilities, but not the primary source. Okay, so this comes to end. Thank you very much for your time and patience. And we'll still continue after this break with posters. Thank you. I'll be still around. Feel free to connect with me if you have any questions or comments.
Thanks. So quick announcement, guys. We'll be break for 10 minutes. 3:20 we'll be back with another session. And one request, humble request, don't go anywhere else around here. There is office working day today. So have a break, tea, coffee, serve just outside, and then come back in maybe 10 minutes. Okay? Thank you.
So I'll turn on
Check. Mic check. Check. Green is. Check.
I think we'll get started. Maybe 1 more minute, people to come and settle down. Guys, let's get started. One is 3:25. We are getting late, so I will get started with the second session, second part of this second session, which is new era of automotive computing, and here we'll be covering more on the radar side of things. Okay. So, Dr. Hall, yours.
Okay, hello. Okay, everything is working. Hello, everybody. So my name is Kostas Doris. I'm Greek in origin and live in the Netherlands, spending a lot of time of my life working on millimeter wave radar. So today we're going to continue our tutorial, moving into and zooming in a deep dive for millimeter wave radar. So I hope when you get out of this room, first of all, you still stay awake. There's a lot of material here to share with you, but also you understand a bit about how it is made. So we talked about what we need, but how do we make it? So for that, we will start a little bit inversely. I'll show you a small video to understand a little bit of how it is used in practice. And then we will really start building up from the ground all the understanding for radar. Okay.
Imaging radar is important today because it's a new key technology for building safer cars. It allows the vehicle to travel in conditions where lighting is poor or the driver has a hard time seeing, so hard rain, light rain, fog. Cases where the driver can't see well, the radar can still see, and then from that to make the safest driving decisions that's possible. Autonomous vehicles are definitely in our future, and they will become the norm when they become extremely safe. We need sensors to continue to mature, and one of the key sensors is imaging radar.
Hi, I'm Robert Carter, Field Applications Engineer for NXP Semiconductors. Today I would like to introduce you to a new imaging radar sensor that we have mounted to our vehicle. This sensor is powered by an NXP radar chipset, and it's developed by our partner Cubtech. Our chipset consists of an S32R45 radar processor and the industry's first dedicated 16 nanometer imaging radar processor. These processors deliver unparalleled computation power for highly efficient real-time data processing at low power dissipation. To provide data for the digital signal processor, there are 4 cascaded RF CMOS TEF 8200 radar transceivers. These transceivers provide 2 times RF performance improvement for enhanced sensing. 4D imaging radar refers to a radar that measures 4 key parameters of objects that the radar can see in its field of view. The first one is range, or distance between the radar and the object. The sensor in our case is actually detecting short range and long range simultaneously. This capability is due to a sophisticated antenna working with the hardware acceleration on our processor, which provides the processing power to process different modes simultaneously. One of the next things that is measured is the velocity or speed of the object.
The radar can determine the difference in velocity between the vehicle and the object. This information is critical, for example, when executing automatic emergency braking, performing adaptive cruise control, or for making safe driving decisions associated with route planning. Another key parameter that is measured is azimuth angle. This measurement describes how far to the right or to the left a detected object lies from the center line of the radar. When multiple objects are in close proximity to one another, imaging radar provides sub 1 degree azimuth resolution so that these objects can be separated from one another. The final dimension is elevation angle. This is a measurement which allows the radar to calculate the height of an object above the road surface. The radar can determine if objects it detects are safe to travel over or if they need to be avoided. One key use case for this parameter in an imaging radar involves detecting an overpass or bridge structure over the roadway while at the same time detecting if the roadway beneath the structure is clear for safe travel. All four dimensions taken together allow the radar to expertly map the scene in front of it. This information can then be used to alert the driver of the vehicle so safe driving decisions can be made. Today, NXP has a leading position in automotive radar. Through our continuous innovation in millimeter wave design, radar signal processing, and advanced algorithms, we will continue to develop products that will keep us in an industry-leading position for years to come.
That's let's call it a visual aspect of what an imaging radar is. So we're going to now build up step by step all of the understanding of how we get there from the basic principles to the most advanced implementation. Let me just get back to the presentation. Okay. So, quick recap on the problem statement. It is a fact that actually more than 90% of the accidents today take place because of an issue related to a human error. And that has a devastating impact, not only in terms of financial aspects, that you have to pay insurances and all that stuff, but it has a human aspect, and it has also many other implications in terms of even if there are no fatalities, congestion, CO2 emissions, things getting slow. So economical factor, but as well as a human factor. And that's basically the problem that the industry is trying to address, how to take out of the equation the human factor. This is a picture from the Netherlands, and we see here it's covering up to roughly 2016, so it's a little bit outdated, but still the main point is there. So this is the yearly traffic fatalities. And this is actually we start time from 1950. And you see here actually that ever since the car was introduced, there has been a steadily increase of road fatalities. There was a peak, and when step by step certain passive safety features have been introduced, such as the belts, the ABS systems, the airbags, and so on and so forth, you could see this being actually reduced substantially. But there is a plateau here, already reached around 2010. And that plateau cannot be further eliminated with passive safety system. And that's where the whole Vision Zero comes into place, which actually means with electronic means, with active safety, we're going to introduce a sort of a safety bubble around the car that allows the car to anticipate and act through electronics, basically, on all the conditions that could lead to an accident. Pirit already mentioned sometime, let's say in the previous presentation, that there are several levels, 5 levels of automation. In fact, there are 6 levels of automation, and it becomes 7. Level 0, which is not in the picture, it means no automation. Level 1 is where basically you have some basic driving assistance functionalities like adaptive cruise control, lane keeping, basic stuff. Most of the cars, or the new cars, do have that type of stuff. On the far right, you have a situation where you're minds-free, hands-free. That is, everything is being done by the car. You don't need to do anything further, fully autonomous. Of course, today, we're in a very critical transition between level 2 and level 3. And there is this small 2+ introduced here. 2+ means we're having difficulty to go from 2 to 3. There is legal issues, so who's having a responsibility? And there are technology issues. So those are the things that actually kind of slow down a little bit the step to 3. That's why we see in the industry the proliferation of 2+. But definitely there will be a continuous progress towards level 5. Now, when we talk about we need electronics and we need sensors, we didn't yet talk about which sensor. I say I'm advocating radar, but the story is a bit more complex. In fact, you need at least 3 sensor modalities. And here, picture camera, a LiDAR, and a radar. The reason for that is because no sensor technology is perfect, and equally well also economical. Different sensors operating with under different, let's call it physical wavelength levels, they operate in a different way, and they give you different benefits. For example, you take a camera, ranging for a camera is a difficult thing. You cannot detect something if it's moving your direction, even you cannot detect the distance. If you actually move to LiDAR, you're on the other extreme. Ranging is extremely precise, millimeter. This is a millimeter because you really use optical wavelengths, and radar is somewhere in between. If you change space to say, okay, now I'm having something like adverse light conditions or weather, the camera is limited, LiDAR is impeded. This is where millimeter wave technology is shining. But if you want to get colors, yeah, the story inverses. So the solution to actually in the industry to get this picture completed, it means you need redundancy. You need to have failure modes. You need to have control points. Therefore, you need to have all of this. Now, we're not going to be discussing about LiDAR. It's another chapter. Main thing there to remember is that there is a zoo of options, of technology concepts, all of them offering the ability to go down to something like sub-$100 device. That would be the big thing today. You can see some of the big LiDAR systems that Google cars or other things are using. They're having this type of big siding things on the top. Exactly, and they cost $1,000, maybe more than that. So that's something that the industry needs to break down. But that will leave apart, and we'll really focus on radar technology. So radar technology for cars is not new. It started in the 24.5 GHz band, some more than 20 years ago. Typically, it was gallium arsenide type of discrete devices. Here's my power amplifier. Here's my oscillator. Is one antenna, bulky big things. Typically, most expensive cars would have that. Now, at that time, you could see other cars. Let's call it. It was the first level of level 1 automation. Front, maybe some kind of angular field of view for cross detection and let's say detection on the back. It was not before these systems moved into the 77 GHz band. And here I make a small parenthesis. I plot here cubes, or kind of, and you see them consisting of smaller cubes here. That's how a radar senses its environment. The larger the cube, the larger the field that the radar sees, and the smaller cubes, the units, the more refined the granularity of that. Think about it as an analog to digital converter, only that it detects and senses the environment. So as we moved from 24 to 76 to 81 GHz band, suddenly the potential for resolution for increasing the cube while still having smaller, let's say small cube units, increased dramatically because simply we reduce the wavelength. That's plain physics. You can reduce the antennas, but the electronics got in the way. So you made a big step on silicon germanium. You reduce the electronics. So some sense of integration started coming in play. And that's why we really started increasing the resolution, but also the ability to integrate more. So seeing bicycles to seeing pedestrians, so start seeing a little bit more. It was not before, let's call it 2015, that the first RF CMOS products got in the market. That actually the big boost in resolution and the big potential of the 77 GHz band. So when I say 77, I mean 76 to 81 is the complete thing. Actually was unleashed because you could really start utilizing the whole of it. You could start fragmenting, or let's call it separating the applications in corner radars, long range radars, blind detection radars, really optimized You saw the Robert Carter, a colleague of mine, showing imaging radar. That's actually many chips together making a big radar. So all that was possible because with RF CMOS technology, you could actually break the barrier between millimeter wave centric LNAs, PAs, front-end performance and radar processing. Then you have a data converter in the middle, you have a PLL, but all that would actually be brought together. So that creates an avalanche of integration. And today we talk about level 2, level 2 plus to 3. Seeing around the car isn't something happening, seeing smaller objects. Yes, we're not yet on the point to see a brick, pardon, or let's say a tire falling off at 300 meters from a pickup truck in the US. You cannot see that yet. It demands for much more resolution. For that, we need to make further steps to be able to map the environment, to be able to detect localization, to detect pavement steps, to detect small things. So there's a continuous evolution here. And we went from 24, 79, and then there will be more steps in the future that you will see at the end that is being cooked, maybe moving to 140 gigahertz and so on. So an evolving landscape. So how to do all that increase in resolution? First of all, let's have a look at the type of radars and their requirements. So you see here different code names, and there is a sort of a range for a given radar function, and also field of view. So if you wanted to do some kind of automatic emergency braking, you need a very long distance to detect, but you need a narrow field of view. If you want to have, for example, cruise control, you need still field of view that's large. So you see all over the place, different radars, different type of applications. You cannot afford having for each of these just a totally tailored device. It's devices that cost a lot of effort to make. So you need to have a scalable approach to fill that. So as shown in the presentation, we need 40 performance: azimuth, elevation, azimuth, range, and Doppler, so velocity. Flexible field of view. You need to go long range and narrow. Suddenly you need to change to be wide field of view. You need to track many objects. Resolution. Sub 1 degrees is not something easily done in radar, as you will see later on why. And imagine that you have two cars at 250 meters, 4 meters apart. Already to detect these two, you need 1 degree of resolution. So that's not unrealistic, that number. Apart from the size and the cost, there is a major point coming up: interference suppression. So you have suddenly, you sell so many radars, everybody has them, but you have like 10, 15, 20 radars on your car and you are in a traffic jam, so everybody's blinded. Okay, one might say, yeah, if I'm in traffic jam, who cares? But that's not always the case. You have also high-speed scenarios, you have a motorcycle crossing by, you have a lot of situations. So interference from radar to radar is an important element coming in the industry, and things have to be done to address that. Connect the sensors. All of these radars need to be connected in a car, in a central processor, or in a zonal architecture, and scalable. That is, you make one design, you utilize it for a platform. For automotive, there are 4 things, we call them the robustness tetrahedron, that actually play an important role and differentiate it from typical commercial applications. The first thing is functional security. So you cannot afford your sensor to be hacked. Prit had already described a few things about it, so I'm not going to detail further. Device reliability. That means 0 component failures. You cannot have your car simply failing because of electronics. Though it is the reality, it's a very expensive thing. So that's an important point. You need to have it 10 years down the road. You have a PA that actually has a degradation of no more than half a dB, consistently being used like 24 hours per day. That's not an easy thing to do. Road safety. No human error. Eliminate the human factor. And functional safety, very, very important. You need to trust your sensor. It needs to tell you, I'm ready to go, and you can trust me. And if you cannot, it needs to tell you, you cannot trust me. It's as simple as that. All of those things add tremendous complications on how you make a circuit. Additional detectors, additional functionality, self-test, diagnostics, name it. All of them are trimming down performance. And that kind of sums up a little bit also to an answer to a question I had before, what takes long to introduce in automotive a given thing that in other fields have been introduced? Yeah, it's the complexity of doing all these things. So now we change gear and we really build up the understanding in terms of principles, how we actually do radar, and how then we implement it. So here on the left, we have an antenna. It's radiates, so this is the lobe of the antenna. There's a signal transmitted, is a target, here an echo signal back. And for simplicity, we'll use a carrier wave. You see it's a pulse. You see this signal oscillated at, let's assume it's 79 gigahertz. And you chop it into pulses. So that means when it is dark blue, you radiate, and then you stop, then you radiate again, stop, radiate again. It's a sequence of pulses. A basic equation that dictates the ranging is simply time of flight. In fact, it's 2 times r, because basically a signal hits and comes back. Remember that, it is important for later. So I get my return echoes, echo 1, echo 2, echo 3. And actually, I have a pulse repetition rate. It's called pulse repetition rate, inverse of it is pulse repetition frequency. So this gave me timestamp. By making a pulse, I have a timestamp, which is my time reference. And therefore, I can simply measure the distance of these pulses relative to my transmit pulse, and that would give me the ranging. If only that was that simple. Of course, you have all these attenuation, scattering, phase change, thermal noise, all those physical effects happening in the field. Let's put them aside for now. Think of the main principle. You just need to detect the distance. So on the top left now, you see on the same plot the transmit blue and the receive echo. We have the concept of range resolution. How narrow, how small is the distance I can actually distinguish? Well, you can easily see that if I have a pulse that falls on top of my transmit pulse, I cannot detect it anymore. So in plain words, I need to have a range resolution is dictated by the duration of the pulse. Right? So delta resolution is simply the time of the pulse. Now, if I have a pulse that falls on top, you see it is non-resolvable. That creates a range ambiguity also. So I have a transmit pulse, and it gives me an echo far away. I'm now transmitting a second pulse. Now, who can tell me if this return pulse is not coming from the second transmit or the first transmit? That's the second problem, ambiguous. The other problem is that if my pulse duration is what counts for resolution, let's make some calculations. So I want to have a narrow pulse to increase the resolution. So I need 10 picosecond pulse for 0.15 meters of resolution. Now that's not practical. You need to get nearly megawatts in this narrow pulse to get a distant range of 200 meters. So that approach, conceptually okay, but practically not okay. So we will see that the concept of pulse compression that we will introduce allows to break this trade-off. Instead of having to use very long pulses for energy, therefore you sacrifice resolution, you can use narrow pulses in a different way without sacrificing resolution, but without the needs to go for a peak. So we'll see that in a minute. Another point to remember is I keep sending pulses. So the blue pulse, 1, 2, 3, 4, etc. And I get the return echoes. Anything that I do, processing, analog or digital, it doesn't matter, within the same pulse, it's fast time. Everything I do, taking all the pulses one after the other and operating across the pulses, we call it slow time. When I have a number of pulses, and I say, that's my frame, I define a frame, say 256 pulses. This is my coherent processing interval. We will see later why it's called coherent, but think about it like this. Everything that happens on the scene in this interval doesn't affect the performance of my radar. So the scene might change, but it's so small the time that actually I can still combine all things coherently. That's for now, I think, sufficient to keep you going, and later we will see exactly in more details what coherence means. Now, of course, I get a pulse, but as I said before, there is thermal noise. So I have here This is the time, the pulse of the power of the pulse, and I have noise, and my pulse is hidden into noise. We need to have a certain level of signal to noise ratio to detect, and typical number to remember is 10 dB. Now, of course, if I have one pulse, it's very difficult to have 10 dB SNR for one pulse only. So we will use cumulative, let's say, summation of many pulses to improve the SNR. Typically, you have to really calculate noise power with the formula KT bandwidth and a noise factor of your receiver, and then basically you can get the noise. And of course, the transmit power, the receive power is a complex function that depends on many things. 10 dB is what we need to have in the end for reliable detection. Excuse me. Another important element is accuracy. So I have a pulse, but how can I tell actually which position is it? Because energy is spreading. So there is a link between the accuracy and the resolution, which is determined basically by the SNR. So these two are dependent, but are not identical. So 3 things to remember. SNR is the range resolution, and the combination, of course, defines also the accuracy. I will propose the following. We will do the questions at the end. Many of these questions will be answered, but otherwise we will break the flow, and I'm pretty sure that those elementary questions too, you'll have them answered during the flow. Yep. So here's the Doppler. Doppler is the mechanism we use to detect velocity. Doppler, you know the siren moving of an ambulance, of a police car. If it approaches you, you feel the pitch increasing, the frequency moves away, it's decreasing. That's as simple as that. So I have a wave here. It hits an object, and this object is moving. It's a reflector. If it moves to the left with a given velocity, and assume here normal velocity, no speed of light and stuff like that, then this thing doesn't work like this. So then practically you see it as the wave is compressing. At the same time, you get more oscillations. It feels like a higher frequency. If I can measure somehow that frequency change, then I can detect the velocity. And I want you to really pay attention to the following. So I have, even forget the velocity now, I have a reflector. The wave hits. Depending on where it hits, you have to see the return echo folding back, right? It just simply folds back. So what I will get at the receiving end here will have a different phase depending on the distance. So if I move this a millimeter or 2 or 3 or 4, I will get at the end the same frequency, but actually at a different phase. Now think about it. If I have a moving object that actually gets a signal, a wave reflected, when I receive it, I will see a continuously moving phase. So instead of trying to measure frequency, we'll find a way to measure the continuously changing phase, and from that deduct the velocity. So how this is done is like this. Blue, transmit pulses, red, received echoes. I'm just rewriting the phase, putting in the factor of distance changing as a function of the object velocity. If you simply change keep the velocity in of the object, you'll actually see that practically the factor 2v of the object divided by the wavelength, this is the Doppler velocity. So practically by measuring the phase, I can deduct the vector, the velocity of the object, the Doppler velocity. Because this is changing. Imagine that if I move a lambda over 4, an object, just move it lambda over 4, I get a change in phase of p, pi, p. I'm Greek, so I'm calling it always p. So that means if this thing is moving, this keeps oscillating. The phase is oscillating. So it keeps oscillating up and down, up and down. So I keep measuring the phase in slow time, pulse after pulse. And that means I measure the phase. And if I measure the phase, I'm sampling. This kind of sampling theory behind it. If I sample it with a proper refresh rate, which is determined by this pulse to pulse interval, I simply can find out what the velocity is. So the shorter the pulses, the higher is the velocity I can measure. But the longer the interval is what I need to get the resolution of that velocity accurate enough. So I need very long intervals to get very good velocity resolution, and I need very fast repetition in order to get large velocities. Think about 400 kilometers per hour. If you're on German highway and you have this way 200 kilometers, this way 200 kilometers on the other side, well, they are in different lanes and separated, fine, but still. So that's the type of relative velocities we're talking about. Now, I said before, received power, and received power is a complicated story. So we typically use the concept of the radar equation, which is a translation of the Friis equation of the communication systems, and the radar cross-section to determine conceptually the amount of power received. And this is how it is done. So imagine you have a transmitter. The transmitter has a certain antenna gain. You send power out. It actually distributes all over the space. And then you get also an object. It captures, intercepts some of that energy, and sends it back. This means basically for each case you have 2 times the link distance. That's different than in communication where you have once. This is 2 times. So depending on how far your, let's say your object is from your transmit and receive antennas, you might be operating in the so-called electromagnetic near field or far field. In the far field, typically you have a wave that is flat, and you can actually approximate the relation between the transmit and receive power. So this is the receive power you get. You're sending some transmit power that you see here. I have a gain of my receiver, gain of my transmitter. I have the wavelength factor in, and I have the distance on the power of 4. That's the important point. Energy reduces substantially as the distance goes far away. And the factor that I will describe in a minute, the radar cross-section. This is far away, the far field regime. If you operate close by, in many cases, even automotive radar operates in the near field regime, in the 5 meters. But for sake of understanding, assume for the rest of the presentation we're far field. If you are really close by, so NFC, near field communication, this is a different story. So they operate on really near field, and those formulas do not exist, do not hold. So we keep in mind here that we have the R in the factor of 4, distance counts in the factor of 4, and there is this factor here, sigma. This is the radar cross-section. So here how it means. So an object interacts with electromagnetic waves, it captures some of it and radiates part of it. The amount of energy that an object will intercept depends on the area. That's why we call it cross-section. It's a kind of an imaginary area. However, also the material properties have an influence to it, and also the actual granularity or the shape of the object. So you will actually see that if you take an object, such as a human, and you radiate from different angles, you will see the blue line giving the typical reflected back energy, intercepted and irradiated back. And you see a bicycle here, you have a different function. Now, this is an important parameter in radar design because it actually captures how much of that energy you get. If you want, I talked about coherency before, you are assuming your radar sees continuously the same radar cross-section from any angle you see it, or during the time you see it. Otherwise, we cannot sum up coherently the energy you get from the pulses. Okay, so we have established the radar cross-section. It's usually measured in dB. And then, of course, we go back to the waveform. Which waveform should we use? There are so many different waveforms. The frequency of them, whether you use a pulse, their sequence, how you encode them, so many things. So this is a field in itself. We will focus on automotive waveforms, and automotive waveforms are following they use a subclass that are called linear frequency modulated waveforms. This is where we focus, and they have some attractive properties that actually translate to implementation as well as to real radar performance indicators, such as ranging and velocity detection. So let's now zoom into these waveforms. First of all, we need to move from a carrier wave to the frequency modulated wave. So here's the pulse with a fixed carrier frequency. You see here, we start with a given frequency, F0, 76 gigahertz. And as And during the time of the pulse, we're increasing to, say, 77 gigahertz. So that's a chirp. This is time versus frequency, and this is actually the time domain equivalent. The beauty of that is that you now have two aspects. On one hand, you have the duration of the pulse. It starts from here, it ends here, which determines your energy of radiation. But you also have the frequency of the pulse changing, which determines your resolution. So you have decoupled practically range resolution from distance. That is how far you go. We use these plots typically to show a chirp. And you see here, this is an echo, so it has a time delay. This is an original chirp. This is a time delayed chirp. We call them chirps from the birds that actually are chirping and they're increasing their pitch. That's the only reason why we do so. Now let's move to the FMCW stretching processing principle. So this on the left, you see a typical FMCW radar architecture. I have my fractional NPLL. It generates the chirp, this curve over here. Typically, this is done at, say, 10 gigahertz, and you upconvert it to 80 with a multiplier. Then you transmit it. The same frequency. It's an IQ modulator in this case. You do some phase control for other things that I will explain later. But the same signal you use for demodulation. So you hit a target, it comes back, and you demodulate it with the same signal. And now let's see what that means. So I have my transmit signal, and I get my echo. At a given moment in time, when I demodulate it in this down-converting mixer, I see the difference. That's what the mixer does. So practically, I translate this RF or millimeter wave signal into a baseband signal. This is close to 80 gigahertz, this is close to 80 gigahertz, this is close to 10 megahertz. And this oscillating signal is the footprint of one target, resonating, oscillated in a fixed frequency. Now that's fantastic, because now what I've done is I have connected the time of flight, which is this delay, with the chirp bandwidth, which is actually, this is the bandwidth, and the chirp duration. So the ratio of the bandwidth of the chirp duration times the time of flight gives me the bit. So I can now measure with an A to D converter this oscillated signal. And I have the distance. And then I can do the velocity processing as well. So that's the whole thing. Everything is based on that very simple principle. If you understand that, you understand the whole of FMCW ranging. I'm sampling it, so I'm making an FFT. Now, that gives me also another interesting property. So again, the same chirp. I don't use the triangle here. So this is the transmitted chirp, the blue one. And I said, we're using an ADC. An ADC has typically a bandwidth up to of Nyquist. And then beyond that, you have aliasing and stuff. Now imagine the following. The more I delay, I have a second target, green, and a third one, target 3. You see them, and when I demodulate, you have the blue signal. So if I have target one, the black one, very nearby to my transmitter signal, it's large. Frequency domain you see is here, large. Then I have a green signal. It's a bit further away, it's smaller, and a red signal, which is beyond my fs/2. I call that the maximum range, the maximum frequency that the ADC has, which corresponds to the maximum range I will detect. I put in low pass filter, and everything else is out. So I've solved the ambiguity problem with just a high pass filter. It's as simple as that. And I can also put a low pass filter, and I can eliminate very strong nearby targets. The signal I have remaining, I just create an FFT on it. And basically I have my radar detection. All of the information I have is on the FFT, the amplitude, the phase, and so on. So that's the stretching property of the FMCW signals, and that's why it is so power efficient, is because you translate a problem from 80 gigahertz to a problem that is on megahertz, 10 megahertz. And then you do basic FFT, high pass filter, low pass filter, and you're done. Now, you can do that in an automotive application like radar. You have a frame rate, typically 40 milliseconds. This is safety, meaning that every 40 milliseconds, you have to refresh your image of the environment. So you have, roughly speaking, 20 milliseconds for acquiring data, 20 millisecond number crunching to get your data out. You could have a single signal, a chirp, going for 20 milliseconds. And you can actually do some basic functions there. But in automotive, we're not using this. Where I'm using many small pulses. Small meaning, like instead of having a 10 millisecond pulse, I'm using a 20 microsecond pulse, but many of them, because that gives me redundancy. It allows me also to decorrelate low frequency noise aspects from high frequency noise aspects. So we'll be talking about the fast chirp principle. It means it's a chirp, yes, but it's fast, meaning it's microseconds, it's not milliseconds. That's the fast chirp. Now, with that in mind, we're going to see now what happens after the ADC. So first of all, we detect range. So here I have the FFT bins for a given chirp. This is the second chirp. This is the third chirp, and so on and so forth. I can plot the FFT data here. You see here radial distance, but actually it's the FFT step. A range bin is an FFT, is a range step, right? And here you see the chirp index. I have 250 something chirps. And I see my target fixed at a given distance, 20 meters in this case. All right. I can see 3D, and you see the target picking up. When I do an FFT, I have a processing gain because I accumulate pulses. I have an SNR improvement, which is proportional to the number of samples. So I have an SNR of my receiver, and then on top of that, I gain in SNR by the number of the chirps. And you see the target. Now let's go to the next step. I do the Doppler processing. So remember that I get my pulses and I want to detect the phase, and the phase is oscillating because the object is moving. So with the FFT, I make a second FFT. The second FFT operates across, let's say, the slow time. So you see the same chirp here, the same object, because it's moving, it has an oscillating phase. So doing the second FFT, this time I do it across the same range bin, but on different pulses. So at first FFT horizontally, second FFT vertically. When I do so, I suddenly realize I have a second target. Interesting, because FFT doing twice means also a second benefit of SNR. That's a further means to detect signal because it lowers the frequency, so the noise even further. And of course, I said before, there are some formulas, I'm not going to explain them, but principle is maximum velocity requires high pulse repetition rate, and maximum resolution, so really high resolution requires a long measurement time. This is a trade-off. And now here visually you can see that in the first FFT, the second target is missing, but by the benefit of the second FFT, I can detect also the second target. The next thing is we need to put a slicer, a limit. We say, look, everything above 10 dB SNR is a target needs inspection. So then I define an layer where we say, look, this is my threshold, and often that threshold is automatically adjusted with what they call a constant failure alarm rate. I'm not going to get into the details, it's a topic in itself. In the end, what you need to determine to understand is like we have false alarm and we have reliable detections, and there is an optimal between the two. So once this is detected, then basically you can have a sort of two-dimensional map where you have the range and the velocity, and each dot represents a target with a given range and a given velocity. I mentioned before that we need, roughly speaking, 25 Hertz, 40 milliseconds for a complete frame. And that's 50% available to collect data, time and frequency, and 50% to let the front end cool down because this is really getting very hot. And in the meantime, to get a processor, get the data and measure them and give us target lists. Okay, so far we talked about range and velocity, but there is more. And that more is the angular resolution. So imagine I have a transmitting signal coming from a car here and two cars at, say, 250 meters at 4 meters distance, moving with the same velocity. There is no way you can tell if it is one or the other car by simply the range and velocity, because a radar measures radial velocity. So you need angular information, and the only way to obtain it is to use multiple transmitters and receivers to create an array and beamforming techniques. Typical definition of angular resolution is the capability that a radar has to detect two targets. Usually you actually count the peak of the lobe of the beam you're creating in the 3 dB point actually, and then that distance actually defines your resolution in the angular domain. Basic phased array type of analysis will tell you that, okay, I have a large number of antenna elements. Imagine one transmitter, multiple receivers. If you want to get 1 degree of resolution, you need roughly, what is it, more than 128 elements. That's a lot of elements. That's multiple watts of power dissipation. It's not straightforward to do that. So we need a better technique to simplify that problem. So what's the principle, first of all? So here is my transmitter from a car far away. Let's assume I have a linear array, one transmitter element here, multiple receiver elements at a given distance. So this is called a linear antenna array. If you assume you're in far field, so your plane wave is it's actually a plane, and the frequency is not very large of modulation, so practically you get a linear relation between in the receive signal. So if I have a signal hitting a receiver on the left side compared to a signal coming on the right side, you will see a time difference proportional to the distance of that, let's say, base of the triangular. You can use basic geometrical properties to actually link the distance to the angle of the object. So now we need to measure the angle of the object. And this angle of the object is measurable by realizing that actually every single element here, in fact, is sampling the wave in a fixed manner. So if I avoid aliasing, so I put them in lambda/2 spacing so that I don't have an inversion of the phase of the signal, I can actually capture for the same wave different points of that, let's call it phase oscillating signal in the spatial domain. So now it's not in time domain, it's on the spatial domain. Every element here has a different fixed phase difference compared to the previous. So what we do now is we create an array, one transmitter, many receivers, many ADCs, and in fact, I can measure the phase as a function of the element. So I create a vector which has the phase difference. This is the element distance, it's a fixed element distance, and has some function here which determines the intensity of the signal I'm getting. So forget it for now, simply assume you get a high quality signal reflected. So if now I do an FFT analysis on the spatial domain, I can actually get the phase of the signal. The longer my array, the narrower the response. Again, it's Fourier analysis implemented now in the space domain. It's the same thing again. There is a bit more on that. There can be multiple different, let's call it algorithms to do direction of arrival estimation. We stick to the basic large array, you get the angular resolution you need. But large array means also large cost. It's very difficult to implement it. So we will now go a step further and introduce the idea of a virtual array. So not a standard array, it's a virtual array. What is the idea about? Imagine I don't have just one transmitter and many receivers. I have one transmitter and a second and a third and a fourth, but they are offsetted. So now from this transmitter, I get 4 received signals with different distance from here, 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 and here. But from the other transmitter, I get a different distance. So I can have a multiplication of the type of different paths by using more transmitters. In that sense, you create a virtual array, which is a convolution in the spatial domain. So for this transmitter, you see actually from here, you get these guys over here. From this one, you get these 4 guys over here, and so on and so forth. So that's a virtual array. What's the advantage of it? If you want to have 16 elements, with a standard approach, you need 16 receivers, 1 transmitter. With this approach, you need 4 transmitters, 4 receivers, so half the elements, 8 versus 16, and it really grows if you go further. There is a catch here. First of all, of course, all those elements, they need to be close together. so that it's coherent. You see the target with the same RCS. You don't see a different target if you go a bit on that side or a bit on the other side. It needs to be the same, right? So it needs to be small. Second point is that you have to distinguish which transmitter signal are you having from. Is it from 1 or from 2? How do you do it? If you have an FMCW waveform, you send the same signal everywhere. How can you tell? So you need to put some functionality into the waveform to encode it. Okay, so that's a different thing you need to do. Now complexity starts building up now. Okay, I need to distinguish. How can I distinguish? I need signal orthogonality, and I can do it in 3 domains. Time, meaning transmitter 1 is allowed to transmit. We wait, transmitter 2 is allowed to transmit, and so on and so forth. That's time. Frequency. I split my band. I have 1 gigahertz, and I split it in 4, 250 megahertz. So I allow transmit 1 in 1 subband, transmit 2 in the second subband, and so on. Option 3, I encode it. I put a bit stream, like in communications, and I can deduct it back actually with the same pseudo-random function, and I can. So these are the 3 principal functions. Let's have a look how they look here. So first, don't focus on the text, focus on the visual. Time domain multiplexing means that I have, in this case, 4 transmitters, 1, 2, 3, 4, different colors, one after the other. Frequency division means I offset them at frequency, or I can create a time offset, a little bit of time delay, and that in the baseband creates also a frequency offset. Encoding, I can do 1 transmitter with a fixed phase, and the other one I can keep alternating the phase, or give a specific phase sequence from a chirp to a chirp, or I can do pulses where I modulate the phase continuously. That's phase coded radar. Now the thing is, well, this is fine, but there is no perfect waveform. Everything has a trade-off here. So if I take on the first one, when I transmit 1, all the rest are shut down. This means I can only use the ranging that 1 transmitter offers. So I'm missing the power of all the rest. So yes, orthogonality is simple here, but it costs me a lot of range. If I use these guys over here, I need to multiply my baseband frequency. I'm really splitting the baseband. That costs me a lot of power on the baseband. If I use Doppler division, then I multiply, actually I split my Doppler. I separate them here in the Doppler domain. So it costs me velocity. There's no free lunch. You have to give something to, so there's compromises to be made. And that introduces trade-offs. Now, what's the best waveform? No one can tell. There are some strong points on one for given applications compared to others for other applications. So you have to choose and optimize and design your system for the use case you're dealing with. So now we put all things together. We created the radar cube, and hopefully now you understand a little bit the first picture I had. So you have your range gates, you have your velocity stuff, and you have also multiple elements, multiple antenna elements. So you can do direction of arrival estimation, and you can also get even more FFT benefit because this is also an FFT. And for each cube, I have a sensitivity vector, meaning how good SNR I have for this data point, for this cube. And this see it as a sort of a continuous refresh. So it's an ADC in a radar definition that you keep quantizing the field in multiple dimensions on a given rate. So to summarize, range detection, you use time of flight. Angle of arrival, you use coherent MIMO in virtual arrays. Velocity detection, you use Doppler. And sensitivity, you use, practically you need SNR for it. And for each of these 4, there are some primary relationships, proportionality with physical aspects like the time of my waveform or the wavelength. And there are some regulated type of dependencies. That is, yes, range resolution, I can increase the bandwidth 10, 20, 30, 40 gigahertz, I can increase the resolution, fine, but I'm not allowed to because now they specify that the radar band is between 76 to 81. Deal with it. You cannot increase further. So next to this sort of overall binding limitations, you have the trade-off between the 4 domains. If I want maximum range, I need a lot of power, longer pulses. I use pulse compression to decouple it from resolution. But then if I want to do velocity, I need shorter pulses. And I need long chirp sequences for resolution, but long chirp sequences get my system incoherent for MIMO. So there's always these cross-domain dependencies. You have to, as a radar system designer, so the system design stops here. You operate in this level. So we'll go to the next level now, to the perspective of the IC designer. Okay, so IC designer typically doesn't understand all that, takes it as a given, gets some specs, says, okay, but reality is that there is an interplay between IC design and system design. And now we have to understand a bit more about circuit implementation. Let's go back. So this is the radar transceiver architecture. Remember, transmit, receive. We get our baseband signal ADC. We do the windowing for FFTs, the 3 FFTs, and that's your target list. And so on the waveform level, the radar designer needs to choose the type of waveform, long range, or mid-range, or a short range, depending on the bandwidth. Remember, long range, there is no need for you to send 4 GHz pulses to get 4 centimeters resolution on a car to 150 meters. It doesn't make sense to spend all that power. So you would use maybe 250 megahertz so that you get, something like 15, 30 centimeters. That's good enough. And then use the margin you have to do MIMO, so that you split your band. So you can play out in a time frequency domain. You segment the whole, let's call it available time frequency product you have, and you plan your waveforms. On the IC architecture antenna, then you need to choose the right architectures. You go into the block level, the right topology for your PLLs, ADCs, and then in the end to implement it in a given technology, which is 22 nanometers, 28 nanometers, 40 nanometers, cubic, bipolar, silver, germanium, name it. It's up to you to choose what's best. But that has a consequence on what you implement here. So a few years ago, around 2010, me and a few of my colleagues, we kind of said to our management team, and then went to some tier one and said, look, guys, we can make RF CMOS for radar. And they were laughing at us, practically laughing at us, because it was unimaginable. You need high supply voltages, you need reliability, you need high output power. How can you make that with CMOS technology? Well, yes, you cannot make it with CMOS technology if you do exactly the same. So you have to switch off your mind and turn it on again to do things in a completely different way with a different technology. You have to combine and use all the degrees of freedom. An application allows you to match technology to the waveforms. So let's take an example. This is a benchmarking of FTF max with ID, so current density. And you see here the black part is the technology, silicon germanium. It's millimeter wave optimized technology in an XP. And you see it does have a higher FT than 40 and 28 nanometer CMOS. But you also see that it generates this at a much higher current density. So now I can go back and say, you know what? I can use a 40 nanometer CMOS, and I can operate my devices at a much lower density. They're fast enough, not in peak power, in peak frequency as good, but they are fast enough, but they give me the advantage of low power. Low power means I can utilize that to reduce losses, so I don't need to generate all this output power. So for example, that's kind of a benchmarking and way of thinking. So you use a nanometer CMOS technology, but you also try to minimize losses so that you don't have to generate so much power. So look at this device. Here is transformer at 80 gigahertz here. So you can take a plain vanilla architecture, not optimizing return paths, the windings, and everything that has to do with reliability and performance at higher frequencies. And you can actually do an optimized one, and you see a quality factor, which is a factor of 2. Now, keep in mind the following. A radar transmitter has a power efficiency in the order of, if you're very good, maybe 10%, 7%. So if you spend a watt, you get maybe 100 milliwatts of signal power. So every dB you spend, you lose actually, because you didn't do a good implementation of your transformer or whatever. You have to multiply by 10 the power you need to generate to compensate for it. So inversing the approach, try to optimize your devices for minimum loss. And then you don't need to generate enough power, and then you open the path for the CMOS technology. And that's the approach. Here you see another example, matching and impedance transformation. At these frequencies, you always use matching networks, impedance transformers. So you can use an LCL line, so that's an inductor capacitor line, or you use a transformer, and there's a world of difference in terms of the power. So for the same initial power, you have significantly less losses, and also impact of tolerances to process variation. That's another element in CMOS technology. Process variations typically lead you to have from a corner to a corner a completely different technology experience. So to make a device that can withstand 150 degrees Celsius to -40 and process variation, matching, slow corners, fast corners, everything, it's a daunting task. So you have to use those type of topologies that actually are robust to these variations. You specify your product for the worst case, worst corner, worst temperature, but in most cases you use it in typical cases, typical temperatures. So that's a big difference. So let's look at the transmitter. The transmitter has a function called phase rotator. A phase rotator means I have a wave at 80 gigahertz and I'm changing its phase. We've seen before, we can use that to embed coding, phase coding, to embed Doppler division multiplexing and so on. It's essential for beamforming and it needs to be very accurate. Then there is a power amplifier. You see a package interface here. That's an important function. From the output of the PA to the antenna, there is a path, there is a transmission line, there is a ball, there is an RDL line. So there is stuff in there that eats power losses. So you have to minimize that. This function is to optimize for reliability, electromigration. You need to put here a BIST function. So BIST means self-test. You cannot test these things at wafer. You cannot test easily at tester. It's a tremendous cost. So you need to have it self-tested. So you need to use transmit signal, put in the receiver, measure it, guarantee performance, guarantee everything is completely self-tested, and also put functional safety. If I have my package broken here, I need to be able to tell to the system, I have no connection from the PA to the antenna. Don't trust me. So you need to put the circuitry that actually does that. And all of those things eat a little bit, a dB here, and another dB there, another dB there. And that's what makes them, in the end, very, very complex. So these are just typical examples of output power. You see here one of our chips shown in the video at 25 degrees, 135 degrees. There is a difference. Still, you have an ample, let's say, a surplus of power far beyond the 10 dBm typically required to really get your link budget in place. And phase coding, this is a 80 gigahertz 6-bit converter, and this is typical plots for different frequencies. So close to half LNSB at the 6-bit level is something like 5.6 degrees of resolution. Similar things to the receive function. You have on the other side, so you get your antenna package interface, your LNA, down-converting mixer, high pass, amplification, low pass, and ADC. You use the high pass function here to eliminate strong blockers. Remember the distance in FMCW stretch the pulse compression function. A target that is close by is usually the biggest. You know, remember the R on power 4 function. So if you have a truck at 5 meters and a bicycle at 10 meters, you have a bicycle significantly smaller. That's one. That's 30 dB difference. And you have the 10 meters distance. That's, you know, you can calculate how many dBs, like 30, 40 dB further. So a strong target nearby, you have to find a way to kind of put it aside. And that you do with this filter. You don't care that much for this very small. A bumper, you put your radar behind the bumper, that's killing in terms of reflections. You need to filter it out. So that's the type of function. And what I call here DDS BIST, you need to be able to guarantee the linearity, functionality, SNR, name it, of your receiver. Now, phase noise is really, really important on radar. On the left, you see phase noise, a typical carrier. That's a typical phase noise plot. Frequency, distance to the carrier. This is 1 megahertz, very important frequency for radar. This is typical up to 400 kilohertz region, dominated by the flicker noise, and then further on, this is the loop of your PLL, and then it goes down. The good thing about radar is that you use the same transmit and receive signal. All right, that means if I'm sending a noisy, contaminated phase noise enhanced, let's say, signal on the transmit side, and it reflects on a radar big truck in front of me, I don't care, because it's the same signal I use to demodulate. So I can take it out of the equation. This is typically factored in a high-pass filter function. So you can see the radar phase noise of a PLL, and you have to apply a sort of high-pass function here, practically meaning you don't care too much about this. But as the distance increases, that effect starts becoming blur and blur and blur, to a point that at a given distance, you cannot count it anymore. And that's where things get really difficult. So here I have a typical use case scenario. You have a motorcyclist in far distance. You have two targets in front of it. It's a long range. So at long range, the phase noise, you see kind of oscillation thing, is because of the sync function here. At far distance, you don't get the attenuation. So you have a large target or two targets here and a smaller one that can be masked. So that's the typical long range imaging radar scenario you want to avoid. This is a chirp. Let's move on how we implement the chirp function. So this is a chirp. You can see here it starts at 0. 0 means it's 77 gigahertz in this case, and goes up to more than 4 gigahertz, so 81. Actually, maybe it's a bit more than 4 gigahertz. And you can see how linear that has to be and is, and how quickly you need to repeat it. This is a chirp sequence, 16.8 microseconds, 4 gigahertz. Now, let's look first on this function. Remember the bit frequency I said after the ADC, you get an oscillating signal footprint of your target. This is determined by the bandwidth of the chirp and also the duration of the chirp. So I use a steeper bandwidth to get higher resolution. Automatically, I get a higher bit frequency. I get a smaller chirp for getting my velocity in place, or for MIMO, then I get a higher bit. So this combination, so height of the chirp, duration of the chirp, is driving the evolution of radar, and therefore the PLL is a fundamental function for the performance of the radar. Not only you need to have low phase noise, you need to be able to implement wider bandwidth chirps and very fast. And there are all sorts of dynamics in the loop that make your life difficult when you want to simply switch off a chirp and then start again. We'll not get into the details, but that's a big problem statement in loop dynamics. How do you get this thing actually repeating itself very linearly? The typical approaches are, again, you use the type of properties of the waveform. To make a small parenthesis, remember we're setting a chirp, which is frequency modulated. So on the transmit side, in order to utilize that, we say, look, why don't I compress my chirp? So I can amplify that to I don't care about amplitude resolution. So I compress it hard, so I don't care anymore about amplitude noise. I don't care about linearity. That's the way to utilize the waveform to match it to circuit, because if I amplify and saturate it, I don't care about process mismatch. So the property of the waveform I use to design a circuit that is robust to process variations. If I want to do a silicon germanium chip with 5 volts or have a linear chip, I would have to deal with process variations. So I cannot copy that architecture to CMOS. I simply use the property of the device to actually implement it. And similarly here, I don't need a waveform to be generated at 80 gigahertz, an oscillated signal. I generate it at 10. I have my VCO at 10. I have a high performance VCO and a low performance VCO, which is wide bandwidth. And then what I do, I use an impedance matching network. So I have my saturated VCO output. What does it mean, saturated? It has a third harmonic component. So I tune my circuit to the third harmonic component. Suddenly I realize a multiplication for free. Yes, I need to amplify a bit, but I don't have frequency at 1 over F noise. And then I use a nonlinear component, and I get another resonance at a third harmonic distortion of that component. And again, I tripled my frequency. I don't need to do other type of complex frequency translator with PLLs. So it is this type of nonlinear functions you have to use thinking, what does my waveform offer to me? I can translate it to circuit that allows you to really generate this type of signals. Let's look on this same use case now from another angle, the ADC challenge. The ADC challenge can be summarized as how can you detect small signals? So again, the same formula, same story, F bit ratio bandwidth of the chirp over the time of the chirp and time of flight. So if you want range and velocity and MIMO resolution, you need more bandwidth and you need shorter chirps. As a result, you need an ADC with a wider bandwidth. Okay. You can relate these functions to realize that actually the range, the maximum range, in the end is determined by the Nyquist frequency of the ADC. So I need more sampling rate. I need a wider bandwidth ADC. But at the same time, let's look here on the power versus frequency. So I take this bit frequency here, and this is the Nyquist. I have my large target that can spread easily 30 dB because of the cross section, truck versus car versus cyclist. And I have a long range motorcycles here next to two big trucks. And this is a guy buried in noise. So it's always buried in noise. Now, if I have a weak signal here and I have an ADC, the ADC creates all these nonlinear spurious components, be that quantization, be that harmonic distortion. So they can appear as ghost targets. Now, ghost targets means, yeah, I have an emergency braking down because of the spur of an ADC. That's not good. That's not good. So you need to really make sure you have an ADC with very large dynamic range, very low noise, and very wide bandwidth. And that's the complexity of the whole matter. So I just give you an example here of those ADCs. You don't find these ADCs on Moorman's plot in literature because they typically report a very single high large signal type of value. So, but when you really look deeper, you have to implement low power inputs and then really start looking into here. And that needs to be clean below 100 dBc. And then you talk about 10 megahertz, 20 megahertz, 40, 80 megahertz. So that's not easy to make. Let's talk about the package. So, okay, we put our transmit and receive function. By the way, we need angular resolution here. So you need 4 transmitters, 4 receivers, DSP. So suddenly you realize, hey, my package is increasing. Okay. First thing is, using a CMOS technology has one important benefit. We said we utilized everything we could from the waveform point of view to make it low power to avoid losses. So we make it small. Okay, good. We make it small means it's a small chip, therefore a small package. Now that there is heat, you see here a footprint, heat footprint. You see the 3 transmitters, and you don't see the receivers because typically it's the transmitter generating most of the power. And you see that actually there is a maximum of 7 degrees from actually one corner of the chip to the other. And that's not a lot. And that's thanks to the fact that the CMOS device is distributing the heat evenly. And that's an important property. So you don't have excursion. So you don't need advanced calibration from a cycle to a cycle. You don't have nonlinearity on your PLL. You avoid all that simply by paying attention to reduce power dissipation. And the other thing is, if you don't have a big chip, you don't need special materials. So here you see a wafer level CSP, SiGe device by CMOS. And then this is a 40 nanometer EWB device. This is 4 times a die area smaller to this one. It's like 20% package reduction. But the important thing is, you don't need special material for board level reliability. Here I need to put a special interposer material, underfill. When I do that, I have another 2-3 dB of losses. And then I need to go back to my PA design and say, can you give me another 3 dB? So it's kind of an avalanche. So reduce power, reduce power, reduce power. That's the main thing. Antenna design, go a bit quickly over that. So here you see a Franklin 10-element design. It has weighting here to implement a specific, let's say, elevation pattern here and wide field of view on the azimuth. And that's a typical response here, the red line. And you have to really get the side lobes low to avoid clutter. So I don't want to radiate straight and I get reflections from the ground or from other cars aside because they give me a lot of noise and they don't help. So you have to get your beam properly and only your beam, no side lobes. Put that together, comes to a device like the Barracuda. Barracuda is a code name. We started from the first design with the dolphin. This is Barracuda, and then we keep using this type of big fish or animals, sea animals, to really describe our products. This one is a second generation 14 nanometer RF CMOS transceiver. You saw it in the video. So 4 receive, 3 transmit, ISO 26262, ASIL level B, multiple digital interfaces, fast chirp, and 6-bit phase rotation. So all that in a MMIC chip. But of course, the world doesn't end there. So what do you do with it? Let me show you a typical sensor design. So it has, everything is put into a radome. Radome is a radar dome, where you put your radar and the antenna and everything. And this is important because it needs to be mechanically robust. It needs to have low attenuation. It needs to be dust-free. It needs to actually have the proper thermal capabilities. So you see the chip here, 4 receive antennas, the patch antennas I showed you before, and the transmit antennas. That's the cover on the top, and behind it there is a microcontroller, Ethernet, and CAN FD. So that's a device. You would call it corner radar. It's a single device. So just an idea how it looks like. You have a device over here. It's a field, and then you're using a given waveform. This is the range Doppler plot. You see a target over here. It's a hotspot. You maybe don't see that easily, but that's the red part here sticking out. The rest is noise. There's a bit of noise closer to the distance because of this, let's say, high-pass filtering, that you still have reflections. At 300 megahertz, you see it clearly here as a spot, but if you use the same walking pedestrian, at 1 gigahertz, you immediately see many more detections. You see suddenly your target starts widening. You get many more detections, a much finer resolution. If you put a car moving here, actually you see the same thing. It's much larger, many detections, and you can distinguish even with a pedestrian. Typical tests to show reliability and performance are also assuming the presence of a car in the car. Sorry, the radar sensor in the car. So nobody wants to have this demo car. We showed you in the video, the imaging radar was on the top. There was a demonstrator, but practically needs to be in the car. So it's behind the bumper, and that means attenuation. So what we typically do here is we have this type of structures. This is the board. This is a bumper. This is an anechoic chamber. You will move the distance from the sensor to the bumper to get a little bit of a feeling of the impact. So, and then you can see clearly that you have the bumper and multiple reflections of the bumper. So it's not only one. And then if you do not use a bumper, it's the red line, so it's like 10, 15 dB, depending on the case, of more signal reflected. But there is no influence on noise floor because every reflection coming back is perceived as uncorrelated noise. In this case, the receiver is extremely linear so that you really don't see any impact. And that's the type of thing you need to take care in application. Now, what's the difference between an imaging radar and a corner radar? So I've showed you this box a couple of slides previously. So if I put now this is a colleague of ours, Eike, a co-author. So actually, and you make a range plot here, you are using a corner radar. Basically, you can get a very coarse resolution. Practically, you cannot easily discriminate. You have like 20, 30 degrees of angular resolution. So in a range Doppler plot, you will not be able to see but only just 1, potentially 2 detections, all in the same place. But if now I get many of these chips and I use multiple antennas, receive and transmit, then I can make a virtual array. With a virtual array, I get higher angular resolution, and I can actually have multiple detections. You can really start detecting the type of the hands of a person, extending them, and so on. And if you push it to the extreme, you're able to get the full contour of the person. Thus, the word imaging. It's not that it creates an image; it creates the appearance of an image. Then you go into multimode radars. So you start now utilizing these chips. You see here a board with multiple chips and antennas. Is put in a radome, and then we have waveguide transitions. They go to different antennas, optimize transmitter, antenna array for long range, antenna array for mid range, and for short range. Different waveforms combined together, and of course, complete DSP engine below to make an imaging radar like the one you saw in the beginning. Those things allow you to use multi-modes, wide field of view, scan, adapt, and so on and so forth. So just an example now, here you see there are two reflectors at a given distance. This is the board. You see actually in this particular case, you have something like 1 degree of resolution, 1.8 in this case. From 1.8 further, you can really start clearly distinguishing the object as you're placing them from far away to close. You actually see it saturates 1.8. That's the type of resolution you get with these radars. So what's next in this band? We're not there yet to fully explode the band, so there's still things hopefully we can do. So if you take this board and you see the imaging radar I told you before, one can make the several observations. So there's a lot to do still on directivity, optimizing the antenna domain. And there is a man in the middle here costing a lot of power because this is a discrete waveguide transition. From here to here you go with a discrete waveguide. So you go from electrical domain of the PA to the electromagnetic domain of an antenna via a discrete waveguide. If you could actually put that into the chip, you would eliminate completely all losses. And that allows you to scale down your power dissipation further. Then another point is to synchronize. You see these long transmission lines, right? So all those things you could actually find a way to simplify. The larger the radar, cascaded radar, the bigger the problem. So you have to find a way to synchronize these radars in a cost-effective manner. New technologies to make power efficiency even better, wider bandwidth ADCs, better DSP, they're all welcome. You need to have even faster and arbitrary wave generators. And in the end, of course, you need more digital processing, a lot of smartness into the processor, into the algorithms. Just an example, visual, this is an antenna in package. What we do here is the previous chip, but we put the antenna in the package. And this is used with a RDL concept, is in artificial dielectric. We put many small patches, metallic patches into the package, and with that we can make an array. And that's actually typical corner radar you can make without the complexity of large antennas and cost and losses. This is another example, is a waveguide launcher. So that's the board I showed you before. And this is the transition where you go to the waveguide domain. You see here is the chip, the bumps. You go with a transmission line to a radiator, actually waveguide radiator to the antenna. You can replace all that directly from within the package, having this blue box. It's a special construction with metals you can radiate directly upwards into. And all those are evolutionary steps that it's one of the many that help you still keep expanding and using the potential of the 76 to 81 gigahertz band. And going back to what I said before, we have limitations. This is a potential that the band offers to us in terms of resolution. We cannot exploit all of that. We have a limit, either defined by safety, either by physical sensor size or the wavelength, physical limitations, regulations. How close can you get to that limit? That's your smartness detecting this and technologies you use. And so we are actually into a technology front, meaning that we can push it further, this front, with newer technologies, newer topologies, newer ideas, newer innovations. But there is a limit. There is a limit imposed by physical limitations. When we reach that limit, what then? Then we go to another band. Easier said than done. It's moving from 76 to 78. So this is the cube. We could move to 140 gigahertz. The cube becomes even smaller. We can go to 300 gigahertz. The cube is even smaller. We can do passive imaging. This is a result of a PhD we have on doing 3 to 500 gigahertz passive imaging. You can do LiDAR. This is a video array with a partner we've made. And this is from ICCC, very nice presentation from Sony. Really, you see, it's a pure image with LiDAR. So you can keep scaling up in frequencies. We realize actually that, wait, somebody told me I had a LiDAR, a camera, and a radar, but actually all this is fused. Now this is LiDAR, it's ranging, but also imaging. This is imaging. This is so there is room for a much more refined, gradual, overlapping technology transitions. It's not as simple say I want a LiDAR or a camera. There are many steps in between. That's a topic for another talk. I will not elaborate in this one now. So with that, I would like to close the talk, to acknowledge many people that are behind this. You see me here talking to you, but there's an army of people and experts and behind all these ideas and concept implementations. And for the rest, thank you for attending, and I'm open for all the questions you might have. Yes.
You're detecting the range from the car, and like suppose if there is just a real-time scenario, there's a child. If the vehicle of yours is like at a good speed, like around 60 to 80, and if a child is going on the road and whilst he is walking, suddenly catching the ball, he tries to run on the road. So will that motion be detected in very short span of time from the radar, saying that that vehicle was previously walking, but the speed suddenly goes quite fast, right, while running? So will that radar detect that much?
So you have to ask yourself, how quickly does a child run, and how quickly you make a transition from walk to run, and does this really make a difference in the application? If the car sees a child inside the road, it should already be alarmed. This is a safety critical situation. You should not design the system such that you wait for the kids to run or not run for the car to pass or not. It's already critical because it's in the distance where you cover by running. So there is, besides the sensory element, that is the absolute brute force capability of the sensor. So you would say, okay, I can calculate how quickly is the transition from walk to run. This is so many milliseconds or a second. Then how fast, you can calculate that. But already the scenario you need to build in the car is you have a car next to the pavement. What to do about it? So one thing is the brute force capability of the sensor. Yes, you can sense all that. But the anticipation to scenarios is something you need to put on your high-level stack. Once you detect there is a possibility of a child next to the street that could be jumping in, or a pedestrian in the bus stop that actually suddenly just jumps in. So you should build that functionality in the use case and scenarios in the car, not in the sensor. The sensor needs to give you reliably that there is a child there, and if the child moves, this is the velocity. You can calculate the collision. Yeah.
So the phase rotator is active or passive? It's a vector modulator.
It's a vector modulator. It's an active vector modulator. Yes, there are multiple different ways to do a phase rotation. A passive is also an approach to do it with transmission lines. They have some implementation weaknesses, especially on losses.
So this frequency, the active is better?
Typically, yes. Compact. It's also compactness in the sense of when you can calibrate it. So I can have an active phase rotator with ducts. Actually, it's a combination of duct, but then I don't care about mismatch. I can calibrate it. So I can use more devices. If I use an LC distributed line with multiple switches, you open up the door to losses, to many different things.
You put some redundant element and then calibrate.
You can calibrate. Standard. Let's call it calibration techniques from the duct domain. Of course, implement it in a millimeter wave. You need to measure phase, not current. And that's the tricky part.
And we have the transmitter and receiver on the same chip.
Yes.
So we have the coupling within the chip from
yes.
the transmitter to receiver. So
of
does
course.
the high-pass filter solve the problem?
Coupling is essential to deal with. There is different impact between TX to RX and TX to TX. TX to RX is the most important. Now, first of all, you need to think how you will floor plan it, what distance, and you need to carefully consider the whole grounding at an electromagnetic simulation level. Then you can kind of figure out the level of isolation you can get. The degrees of freedom the package offers you, grounding multiple layers, is essential here. That's one thing. Let's say you do your best and you get a 40 dB isolation, fantastic number, very difficult to get in practice. Then you actually give it to your tier one, he makes a design, and he puts the antennas close by or the transmission, and you get 15 or 20. So there is the on-die problem, there is the in-package problem, and there is your tier 1 problem. So there are different levels. So typical semiconductor levels, what we provide is typically better than 30 dB. What then the user is doing with it, designing their antennas, that's another story. Yes.
Can you talk a little bit more about it's an active sensory, right? You're putting out energy and you're sensing it. And as you pointed out, there are other cars can have active energy, maybe infrastructure can have active energy. So where is, I guess I'm trying to think about where is this world going from an interference point of view? And also, is this band isolated for your use, or are there, I don't know, police guns, whatever else? What other applications are using this band?
So it is only meant for automotive radar. The first point is, so no other user can use that band.
Okay.
That's the first thing. However, the level of regulation in this band is kind of minimal. It's only how much power you emit, and out of band emission, that's it. Right. And then the type of waveform you use is your degree of freedom as a tier 1 typically. So I'm coming from tier 2 semiconductor. I make the equipment for them to use a given waveform, and they make the waveform. All right. And that's a differentiation element. One can do a better waveform than the other. Now, when you talk about interference, it's a very multidimensional problem. So you can say, if I had everything regulated, I split my band in chunks, I can use this one, then actually I don't have interference, so I don't emit exactly. Okay, this is not done. Right. What typically is done is you can have patterns of chirps. There are efforts in the industry to standardize, at least get some basic understanding between tier 1s. There are open calls for that one, where you can say, look, I'm having a car with a front range radar, and I see a car with a blind detector, a rear detector. So let's agree that front is always polarization vertical, and back is another polarization. So we're not interfering each other. Or let's agree we have a kind of compass base. Depending on the steering I get, I change my bands accordingly. So there are some kind of efforts, but in the vast majority, everybody does something. And that's why there's so much awareness being created.
Doing that part of it, what about reflection from the environment itself? Tunnels and other structures which cause, I guess, double bounces back or something like that.
But the R on the power of 4 is your friend here.
That's right.
So if you get a second reflection which is twice the distance, A, it's severely attenuated. 2, you filter it with high pass filter, you don't see it.
Right.
So that's the easier part of the equation. The most difficult is, okay, I have a radar of a car emitting to my radar. And then, is it coherent? No. So we have a slope like this and another slope of the other radar like this.
Right.
For how long does it fall in? If that is that long, for how much of that part is it within the band?
Right.
So all that play a role, making a very...
So, I don't know, one more follow-up question. Sure. So on the actual implementation side, so given all these trade-offs, right, to what degree are you guys thinking about sort of having a analog, digital, programmable architecture so you can play with this space? I guess in my mind, the digital equivalent is you have kind of an FPGA kind of idea where you have a large degree of programmability around a framework.
Mm-hmm.
Right? Yes. So in these architectures, are there thoughts like that?
Yes, of course. For example, if you take the chip generator, you can generate any bandwidth between 76 to 81. Right. You can actually give it any time you want, any slope you want.
Right.
In the ADC, you can program the filtering, the high pass, low pass filtering, the data rate. On the transmit side, you can program the phase, you can program the power. So there is an evolving level of functionality added.
Right.
To enable this type of waveforms that everybody would like. Because I told you, a plot with 3 waveforms means that there is a chip being done with a given time frequency profile, and the next chip is done differently. So you need to have that embedded programmability.
So, and is that programmability done fixed function, or do you see that being updated, just like we do over-the-air updates?
It's been updated per frame. It can be updated per chip.
And so therefore it can be updated based on learning from the environment.
Yes. Thank you. You have an actuated system. You can change it per chip.
We can have one last question from here.
Hi.
Hi.
So I have a basic question. Can you please go to that transmitter slide with the PLL and everything? Yeah.
This one is only the PLL.
No, that one. Yeah. So you are using a PLL to generate a chip, right?
Yes.
Why don't you just take a VCO and a capacitor bank and tune that VCO to generate a chip? Why go into a PLL?
The beauty of a PLL is as a closed loop system. So it tunes out all the issues of process variability and non-linearity of the VCO. You need to have a very linear chip, a very wide bandwidth. So with a VCO, you have to put very advanced calibrations, pre-distortions, and you need to deal with a lot of process variations.
Yeah, but the linearity of the VCO, right? You're talking about the sensitivity to the voltage versus frequency.
Mm-hmm.
That's the linearity you're talking about.
But also the chip, that needs to settle properly, be within a given frequency offset guaranteed.
And that is what the PLL helps.
It's a feedback system, so you benefit by the gain loop to get the linearity.
Okay. Thank you.
Okay, I think we are late, so we'll end the session today. Thank you, Dr. A wonderful session, and great gathering. So we're going to end update. We'll present some memento to our speakers. So
Get another use for the shirt. Thank you.
thanks everyone for attending. People who have not signed, so they can sign here, register for their attendance. And like I said, thanks to all for coming and attending this.